There is a star in the night sky that you have almost certainly seen. It glows with a deep reddish hue, perched on the shoulder of the constellation Orion. You may have noticed it without knowing its name. You may have pointed at it as a child, guided by a parent's hand toward the three bright stars of Orion's belt, and then drifted upward to the faint ruddy glow sitting just above and to the left. That star is Betelgeuse, and it is dying, not in the distant abstract way that all stars eventually die, not in a timeline measured in billions of years, safely beyond the concern of any human civilization that might ever exist. Betelgeuse is dying now. It has entered the final chapter of its existence, a chapter measured not in billions of years but in thousands, or possibly even less. And when it finally collapses under its own unimaginable weight, it will produce an explosion so violent, so luminous, so fundamentally powerful that it will be visible from Earth in broad daylight. It will outshine the full moon. It will cast shadows at night. For weeks, perhaps months, a new light will hang in our sky, brighter than anything any living human has ever seen from beyond our own solar system. The explosion is called a supernova, and the question that haunts astronomers, the question that has driven decades of research and observation, is not whether Betelgeuse will explode. That outcome is certain. The physics demands it. The question is when. It could happen in 100,000 years. It could happen in 10,000 years. Some models suggest it could happen considerably sooner than that, and there is a small but non-zero possibility that it has already happened, that the core of Betelgeuse has already collapsed, that the shock wave has already torn through its outer layers, that the explosion is already underway, and the light from that catastrophic event is traveling toward us right now, crossing the void of interstellar space at 299,792 kilometers per second, and we simply have not received the message yet. We are watching a star that might already be gone. Consider what that means. Betelgeuse sits roughly 700 light-years from Earth. Some recent estimates place it closer to 724 light-years. That distance means the light we see tonight left that star approximately 700 years ago. We are not watching Betelgeuse as it is. We are watching a memory, a recording, a ghost image projected across the cosmos. The star we observe tonight could already be gone, replaced by an expanding cloud of superheated gas and newly forged elements, and we would not know for centuries. Every time you look up at Orion and see that reddish glow on its upper left shoulder, you are placing a bet, a quiet, unconscious bet that the star is still there, that the message of its death has not yet been sent, that the light of destruction is still on its way, somewhere in the darkness between here and there. And here is what makes the situation even more unsettling. In late 2019, Betelgeuse did something that no one expected. It dimmed, not by a small, subtle amount detectable only by sensitive instruments. It dimmed visibly, dramatically, losing roughly 65% of its brightness over the course of a few months. The dimming was so severe that you could see it with the naked eye. Orion looked wrong. Its shoulder was fading, and for a brief electric moment, astronomers around the world wondered the same thing. Was this it? Was Betelgeuse about to blow? The answer turned out to be more complicated than a simple yes or no, and the explanation that emerged raised more questions than it answered, painting a picture of a star in a state of turmoil that may be more extreme and more advanced than anyone had previously imagined. This is not a story about a distant threat. This is not a story about something that might happen someday to someone else's sky. This is a story about a star you can see tonight, a star that has been a part of the human experience for as long as humans have looked upward, and a star that could rewrite the night sky within the span of a single human lifetime. The odds may be small, but the odds are not zero, and the physics does not negotiate. By the end of tonight, you are going to understand what Betelgeuse is, why it behaves the way it does, what will happen when it finally detonates, and why this single star, out of the hundreds of billions in our galaxy, has become one of the most closely watched objects in all of modern astronomy. You are going to understand the physics of stellar death, the strange and troubling dimming events that have alarmed scientists in recent years, the multiple theories that compete to explain what is happening inside this dying giant, and the profound, almost philosophical question that Betelgeuse forces us to confront. What does it mean to watch something die in slow motion across the cosmos, knowing full well that the final moment of death may have already passed, and we are simply waiting for the news to arrive? What does it mean to look at a star and know, with scientific certainty, that it will one day produce an explosion visible across half the galaxy, and to have no idea whether that day is tomorrow or in 100,000 years? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand Betelgeuse, we first need to understand what kind of star it is, and to do that, we need to understand what stars are in the first place. Not poetically, not metaphorically, physically, mechanically, in terms of the actual forces and processes that sustain them. A star is a sphere of plasma, primarily hydrogen and helium, held together by its own gravity and powered by nuclear fusion in its core. That process, the merging of hydrogen nuclei into helium under extreme pressure and temperature, releases energy. That energy pushes outward, creating a force called radiation pressure. Gravity pulls inward, trying to compress the star into the smallest possible volume. And for most of a star's life, these two forces exist in a delicate, extraordinary balance called hydrostatic equilibrium. The star neither collapses nor explodes. It simply burns, steady and stable, converting matter into energy at a rate determined by its mass. Our Sun is one such star. It has been burning for approximately 4.6 billion years, and it is expected to continue burning for roughly another 5 billion years before it runs out of hydrogen fuel in its core. It is a relatively modest star, classified as a G-type main sequence star, sometimes called a yellow dwarf, though it is technically white when viewed from space. Its diameter is about 1.4 million kilometers, which means you could line up roughly 109 Earths across its face. Its surface temperature hovers around 5,500 degrees Celsius. Deep in its core, where the fusion reactions take place, the temperature reaches approximately 15 million degrees Celsius, and the pressure is roughly 265 billion times the atmospheric pressure at sea level on Earth. Under these extreme conditions, the Sun converts roughly 620 million metric tons of hydrogen into approximately 616 million metric tons of helium every single second. The difference, roughly 4 million metric tons per second, is converted into energy according to Einstein's equation relating energy to mass and the speed of light squared. And by stellar standards, our Sun is unremarkable. It is average in size, average in luminosity, average in temperature. It sits comfortably in the middle of the main sequence, the band on the Hertzsprung-Russell diagram, where most stars spend the majority of their lives. The Sun is, by any measure, a perfectly ordinary star. Betelgeuse is not ordinary. Betelgeuse is classified as a red supergiant, one of the largest categories of stars that exist. It belongs to spectral type M, indicating a relatively cool surface temperature of roughly 3,500 degrees Celsius. But do not let the word cool mislead you. That temperature is still hot enough to melt any known material. The reason Betelgeuse appears red is that its surface is cooler than the Sun's. Stars radiate light across the spectrum, and the peak wavelength of that light depends on surface temperature. Hotter stars appear blue or white. Cooler stars appear orange or red. Betelgeuse, at 3,500 degrees, radiates most of its energy in the infrared, with only a portion in visible red light. That is why it appears as that distinctive deep red point in the shoulder of Orion. But the defining characteristic of Betelgeuse is not its colour, it is its size. Betelgeuse is one of the largest stars visible to the naked eye. Its diameter is estimated to be somewhere around 1.2 billion kilometers. Some measurements suggest slightly larger, others slightly smaller, because the star's outer boundary is diffuse and variable. But the central estimate places its diameter at roughly 800 times the diameter of our Sun. Let that number register for a moment. 800 times. If you were to place Betelgeuse at the center of our solar system, in the spot currently occupied by the Sun, its outer atmosphere would extend past the orbit of Mars. The orbit of Mars sits roughly 228 million kilometers from the Sun. Betelgeuse's radius of approximately 600 million kilometers would swallow everything inside that distance. Mercury gone, Venus gone, Earth gone, Mars engulfed. Some estimates, depending on the model used and the definition of the stellar boundary, suggest the edge of Betelgeuse might extend as far as the orbit of Jupiter, which sits roughly 778 million kilometers from the Sun. A single star occupying the volume of space that in our solar system contains the Sun, 4 rocky planets, the asteroid belt, and potentially even the largest planet in the system. Here is a scaled comparison to help anchor this enormity. If the Sun were the size of a standard basketball, roughly 24 centimeters in diameter, then Betelgeuse would be a sphere roughly 192 meters across. That is wider than 2 football fields placed end to end. And Earth, in that same scale, would be about 2 millimeters in diameter. Smaller than a grain of rice, smaller than a single lentil. You would need a magnifying glass to see it. That is the disparity we are dealing with. That is the kind of object Betelgeuse is. Not just big, absurdly, almost incomprehensibly big. Now, here is another way to grasp this. Light, the fastest thing in the universe, travels at roughly 300,000 kilometers per second. At that speed, light crosses the diameter of our Sun in about 4.6 seconds. Light crosses the diameter of Betelgeuse in over 1 hour. Think about that. You could start a timer, and a beam of light, traveling at the maximum speed permitted by the laws of physics, would take more than 60 minutes to travel from one side of this star to the other. If you tried to fly around the equator of Betelgeuse in a commercial airplane traveling at 900 kilometers per hour, the journey would take approximately 4,700 years. Your departure would predate the construction of the Great Pyramid at Giza. By the time you landed, you would have missed the entire span of recorded human civilization. And the size comparison only tells part of the story, because Betelgeuse is not merely vast, it is luminous in a way that dwarfs our Sun. Despite its cooler surface temperature, the sheer amount of surface area radiating energy makes Betelgeuse one of the most luminous stars in our region of the galaxy. Current estimates place its luminosity at roughly 100,000 times the luminosity of the Sun. Think about what that means. Every second, Betelgeuse pours out as much energy as 100,000 suns combined. If you could somehow gather all the energy the Sun produces in 100,000 seconds, roughly 28 hours, Betelgeuse produces that same amount in a single second, and most of that energy is in the infrared, invisible to our eyes. If our eyes could see infrared light, Betelgeuse would appear far brighter than it already does. It would dominate the sky. There is a useful way to think about the relationship between size, temperature, and luminosity in stars. A star's luminosity depends on 2 factors, the surface area and the surface temperature. A hotter surface radiates more energy per unit area, but a larger surface provides more area to radiate from. In the case of Betelgeuse, the surface temperature is only about 64% of the Sun's, but the surface area is roughly 640,000 times greater. The enormous gain in surface area overwhelms the modest loss in temperature, producing a star that is vastly more luminous than our own, despite being cooler. If we were to place Betelgeuse at the distance of Alpha Centauri, our nearest neighboring star system, at 4.37 light-years away, it would appear approximately as bright as the full moon. A single star, visible in daylight, casting faint shadows on the ground. From that distance, it would be an awe-inspiring and somewhat terrifying sight. A bloated, ruddy disk visible to the naked eye, visibly larger than a point of light, pulsating gently as its surface heaved and swelled, and the energy that Betelgeuse radiates comes at a cost. The more luminous a star, the faster it burns through its nuclear fuel. Our Sun, modest and efficient, will burn for roughly 10 billion years total. Betelgeuse, profligate and extravagant, will live only about 8 to 10 million years. It burns through its fuel at a rate so extreme that its entire lifetime, from birth to death, is roughly 1,000th the length of the Sun's. If the Sun's lifetime were a year, Betelgeuse's would be less than 9 hours. A flash, a flicker, a brief brilliant burn that ends in catastrophe. This relationship between mass, luminosity, and lifetime is one of the most important principles in stellar astrophysics. More massive stars burn hotter, shine brighter, and die younger. The most massive stars known, at 50 to 100 or more solar masses, live only a few million years. The least massive stars, tiny red dwarfs at 1/10 of a solar mass, burn so slowly and so efficiently that they can shine for trillions of years, far longer than the current age of the universe. Betelgeuse sits in the middle of this range among massive stars, large enough to die spectacularly, but not so large that its life was over almost before it began. It has had time to develop, to evolve, to cycle through the stages of fusion that build heavier and heavier elements in its core. And it is those stages, that progression from hydrogen to helium to carbon to neon, to oxygen to silicon and finally to iron, that tell us where Betelgeuse stands in its journey toward the end. But size alone does not make Betelgeuse extraordinary. What makes it truly extraordinary, what makes it the subject of intense scientific scrutiny and public fascination, is its stage of life. Betelgeuse is a star in its final act. It has already exhausted the hydrogen in its core, the fuel that sustained it for most of its existence. It fused that hydrogen into helium millions of years ago. When the hydrogen ran out, the core contracted under gravity, heating up until it reached the temperature necessary to ignite helium fusion, roughly 100 million degrees Celsius. Then it began fusing helium into carbon and oxygen. Then, as the helium was consumed, the core contracted again, heated again, and ignited carbon fusion at roughly 600 million degrees. Then carbon into neon, then neon into oxygen, then oxygen into silicon. And soon, if it has not already begun, it will fuse silicon into iron. And iron is the end of the line. This is the critical point that separates Betelgeuse from our Sun and from the vast majority of stars in the galaxy. Iron fusion does not release energy, it absorbs it. Every element lighter than iron releases energy when it is fused, because the resulting nucleus is more tightly bound than the original nuclei. But iron sits at the peak of the binding energy curve. Fusing iron into heavier elements requires an input of energy rather than releasing it. When a massive star develops an iron core, the process that has held the star up for millions of years, the outward push of energy from fusion ceases. The balance breaks, gravity wins, and the core collapses at roughly 1/4 of the speed of light, roughly 70,000 kilometers per second. The collapse takes less than 1 second, and then the star explodes. The process of sequential burning, this layered progression through heavier and heavier elements, is what defines the life and death of a massive star. Our Sun will never reach this stage. It does not have enough mass. When the Sun exhausts its hydrogen in roughly 5 billion years, it will swell into a red giant, large enough to engulf Mercury and Venus and scorch the surface of Earth. But it will never achieve the core temperatures necessary to fuse carbon. Instead, it will shed its outer layers into a beautiful expanding shell of gas called a planetary nebula, and the remaining core will cool and contract into a white dwarf, a dense, dim remnant roughly the size of Earth, but with the mass of the Sun. It will fade over billions of years, slowly cooling from white to yellow to red to dark, until it becomes a cold, invisible cinder drifting through the galaxy. A peaceful death, a gentle dimming. Betelgeuse will not die gently. It cannot. It is far too massive. Current estimates place its mass at roughly 15 to 20 times the mass of the Sun. Some studies have suggested values as low as 12 solar masses, while others have proposed values as high as 25. The uncertainty matters enormously, as we will explore later, because the mass of the star determines the exact nature of its death and the type of remnant it leaves behind. But regardless of the precise number, Betelgeuse is well above the threshold required for a core collapse supernova, which begins at approximately 8 solar masses. There is no escaping this fate. No process in the known universe can prevent it. The physics is settled. Betelgeuse will explode. The name itself carries history. Betelgeuse derives from the Arabic phrase Yad al-Jazar, which translates roughly to the hand of the central one or the hand of the giant. Through centuries of transcription and translation, through Latin, medieval European, and modern astronomical catalogues, the name evolved through various spellings before settling into its current form. It has been observed and named by cultures around the world for thousands of years. The ancient Egyptians had associated the stars of Orion with Osiris, their god of the afterlife and resurrection. Aboriginal Australian traditions incorporated Betelgeuse into complex astronomical narratives. that connected the sky to the land. Chinese astronomers catalogued it as part of the constellation they called Shen, one of the 28 mansions of the Chinese zodiac. In Hindu astronomy, it was associated with the nakshatra Ardra, linked to the storm god Rudra. Across every culture that has gazed at the night sky, this red star has been noticed, named, and woven into stories. In Western astronomy, Betelgeuse is designated Alpha Orionis, despite typically being the second brightest star in the constellation after Rigel, which is designated Beta Orionis. This apparent inconsistency arises because the Bayer designations, assigned by the German astronomer Johann Bayer in 1603, were not always strictly ordered by brightness. The inconsistency is compounded by the fact that Betelgeuse is a variable star. Its apparent magnitude fluctuates between roughly 0.0 and 1.6 over its pulsation cycle, meaning that at maximum brightness, it does sometimes outshine Rigel, which has an apparent magnitude of roughly 0.13. This variability was first documented systematically by Sir John Herschel in 1836. Herschel, one of the most prolific observers of the 19th century, and the son of William Herschel, who discovered Uranus, noted in his observational records that Betelgeuse appeared to change brightness over periods of months to years. Later observations confirmed that Betelgeuse is a semi-regular variable star, meaning its brightness changes are periodic but not perfectly regular. The primary pulsation period, the time between successive brightness peaks, is roughly 400 days. A secondary, longer period variation of roughly 5 to 6 years has also been identified. These pulsations are caused by the star physically expanding and contracting, like a slow, enormous heartbeat. When the star expands, its surface cools and it dims. When it contracts, the surface heats and it brightens. But this heartbeat is not the steady, reassuring rhythm of a healthy star. It is the irregular, labored pulse of a star running out of fuel, a star whose internal structure is changing on timescales that are short compared to its total lifetime. Modern observations of Betelgeuse have been conducted by some of the most powerful instruments ever built by human hands. The Hubble Space Telescope captured direct images of Betelgeuse's surface in 1996 using its faint object camera. This was a landmark achievement. Betelgeuse became one of the first stars other than the Sun to be resolved as a disk rather than a point of light. The image, though crude by the standards of what would follow, showed a bright hot spot on the surface, evidence of enormous convective cells churning beneath the photosphere. The Very Large Telescope Interferometer in Chile, which combines the light from 4 separate 8.2-meter telescopes, has since mapped the surface features of Betelgeuse in extraordinary detail, revealing a churning, boiling surface dominated by a small number of immense convective plumes. The Atacama Large Millimeter Array, known as ALMA, a network of 66 radio dishes in the Chilean Andes, has observed the material being ejected from Betelgeuse's surface, revealing a complex wind of gas and dust streaming outward into the surrounding space. And then, in late 2019, Betelgeuse did something that captured the attention of the entire world. It dimmed, dramatically, unprecedentedly. Between October 2019 and February 2020, the brightness of Betelgeuse in visible light dropped by approximately 60 to 65%. It went from being one of the 10 brightest stars in the night sky to barely ranking among the top 25. For a star that has been watched by human eyes for at least 5,000 years of recorded civilization, this was unlike anything in recorded astronomical history. The dimming was not subtle. It was not an artifact of measurement or a quirk of calibration. It was visible to anyone who knew where to look. Anyone who walked outside on a clear January night in 2020 and looked up at Orion could see that something was wrong. The shoulder was fading. The familiar pattern was altered. Something had changed. The event was quickly dubbed the Great Dimming, and it triggered a cascade of speculation, excitement, and anxiety that rippled through both the scientific community and the general public. Social media erupted with questions. Was this it? Was Betelgeuse about to go supernova? Were we about to witness the most spectacular astronomical event in over 4 centuries? Headlines appeared in newspapers and on websites around the world. Astronomers rushed to secure telescope time. Amateur observers with backyard instruments tracked the dimming night after night, contributing data to a global effort to understand what was happening. The answer, as it turned out, was neither simple nor entirely reassuring. The Great Dimming was not a supernova, but the explanation that eventually emerged revealed something important, and perhaps deeply unsettling, about the current state of Betelgeuse. It revealed a star in a state of turmoil that went beyond normal variability. A star that was, in a very real and physical sense, tearing itself apart. But before we can fully understand what happened during the Great Dimming, and what it tells us about the future of this extraordinary star, we need to dive deeper into the physics of how a star like Betelgeuse actually dies. Because the death of a massive star is not a single, discrete event. It is a cascade, a sequence of failures, each more catastrophic than the last, accelerating with terrifying speed until the final moment arrives in a fraction of a second. And once you understand that cascade, the dimming of Betelgeuse takes on a very different and far more ominous meaning. Imagine compressing the entire lifetime of Betelgeuse into a single calendar year. The star was born on January 1st. For the vast majority of that year, from January through roughly mid-December, it sat on the main sequence, calmly fusing hydrogen into helium in its core. 11.5 months of stability. The helium-burning phase, when the star leaves the main sequence and expands into the red supergiant we see today, would occupy approximately December 15th through December 29th. 2 weeks of the year. Carbon burning in the core would last from December 30th to sometime on December 31st, a single day. Neon burning would take roughly 6 hours on December 31st. Oxygen burning would last about 10 minutes. And silicon burning, the very last stage before core collapse, would take approximately 1 second. 1 single second at the very end of an entire year. That is how compressed the final stages become. The end does not announce itself gradually. It does not send polite warnings. It collapses inward, faster and faster, until the entire sequence of final fusion stages occupies less time than it took you to read this paragraph. We are watching a star approach that final second. We do not know how close it is, but we know it is coming. And what happens next will reshape our understanding of stellar physics, nuclear astrophysics, and perhaps our understanding of our own place in the cosmos. To put the remaining lifetime of Betelgeuse into yet another perspective, consider the following. The fastest spacecraft ever launched by humanity is the Parker Solar Probe, which reached a speed of roughly 635,000 kilometers per hour during its close passes by the Sun. At that speed, the fastest any human-made object has ever traveled, it would take you roughly 118 million years to reach Betelgeuse. If you had launched such a spacecraft at the moment Betelgeuse was born, roughly 8 to 10 million years ago, you would still be less than 1/10 of the way there. The distances between stars are not just large, they are humbling. They reduce every human achievement, every technology, every ambition, to an almost comically small scale. And yet we can see Betelgeuse with our bare eyes. We can study it, measure it, model it, and argue about when it will die. That ability, the ability to comprehend objects at such staggering distances, is itself one of the most remarkable things about our species. And so we watch. Night after night, year after year, generation after generation, we watch the red star on Orion's shoulder. We measure its light, we model its interior, we debate its future, and we wait for the day when the light changes, when the news finally arrives, when the sky is transformed by the death of a star that has been a companion to humanity since before we were truly human. That day is coming. The physics guarantees it. The only question is whether we will be here to see it. The core problem with Betelgeuse is deceptively simple to state and extraordinarily difficult to resolve. We do not know when it will explode, and our uncertainty is not a small tide gap that a few more years of observation might close. It is an enormous chasm spanning 5 orders of magnitude. Estimates for the remaining lifetime of Betelgeuse range from as little as a few tens of thousands of years to as much as 100,000 years or more. In astronomical terms, both of these numbers are practically zero. The star is roughly 8 to 10 million years old. Whether it has 10,000 or 100,000 years left, it is in the final fraction of a percent of its total existence. But in human terms, The difference between 10,000 years and 100,000 years is the difference between something that might affect future civilizations and something that is completely irrelevant to anyone alive today, or to anyone who will be alive in the next several hundred generations, unless, of course, the lower estimates are correct, and some scientists believe they might be. The difficulty lies in the internal structure of Betelgeuse. We cannot see inside a star. No telescope exists, no instrument has been built, and none is currently planned that can directly observe the core of a star. We can measure the surface temperature through spectroscopy, analyzing the wavelengths of light emitted by the photosphere. We can measure the luminosity by combining the apparent brightness with the distance. We can estimate the size through interferometry, using multiple telescopes to resolve the angular diameter. We can infer the chemical composition by examining spectral absorption lines, the dark gaps in the spectrum caused by specific elements absorbing specific wavelengths of light. And we can estimate the mass through various indirect methods, including stellar evolution models and binary orbital dynamics, though Betelgeuse is a single star without a known companion. But the core, where the real action is happening, where the sequential fusion of heavier and heavier elements is either underway or imminent, is hidden behind hundreds of millions of kilometers of opaque, superheated, turbulently convecting plasma. We are trying to diagnose the condition of a patient without being able to examine anything except the outermost layer of skin. We can see the symptoms, we can measure the fever, but the disease, the inexorable progression of fusion stages that is driving this star toward catastrophe, is invisible. What we do know is troubling. Betelgeuse has clearly left the main sequence. It exhausted its core hydrogen supply millions of years ago and expanded into the red supergiant phase. The star we see today is no longer a simple sphere of hydrogen burning steadily in its center. It is a complex, layered structure, burning multiple elements simultaneously in a series of concentric shells around an increasingly dense, increasingly hot, and increasingly unstable core. Each shell burns a different element at a different temperature and density. Hydrogen on the outermost burning shell, then helium beneath that, then carbon, then neon, then oxygen, and eventually silicon in the innermost shell surrounding the growing iron core. The structure resembles an onion, with each layer representing a different stage of nuclear fusion, a different chapter in the star's inexorable march toward collapse. The key question, the question that determines whether Betelgeuse will explode in our geological era or in a far more distant future, is which element the star is currently burning in its innermost core. If it is still fusing helium in the core, it might have several 100,000 years left. If it has progressed to core carbon burning, the timeline shrinks to roughly 100,000 years. If it has reached neon burning in the core, the timeline collapses to roughly 1,000 years. If it has reached oxygen burning, it has months. If silicon, a single day. The progression is not linear, it is exponential. Each stage is dramatically shorter than the one before it, because each heavier element releases less energy per fusion reaction, meaning the core must burn faster and faster to generate enough outward pressure to support the staggering weight of the star above it. Carbon burning in a star of Betelgeuse's mass lasts roughly 1,000 years. That sounds like a long time, but consider the context. Betelgeuse has been alive for roughly 10 million years. 1,000 years is 1/10,000th of its total lifetime. It is the equivalent of the last 52 minutes of a calendar year. And the stages that follow carbon burning are even more extreme. Neon burning lasts roughly 1 year. Oxygen burning lasts a few months. Silicon burning, the final stage before the iron core reaches its critical mass, and the entire structure collapses, lasts approximately 1 day. 24 hours, 1 rotation of the Earth, then everything ends. In 2020, a team of researchers led by Meredith Joyce at the Australian National University published a study in the Astrophysical Journal that attempted to pin down the evolutionary state of Betelgeuse with greater precision than any previous effort. The study used a technique called asteroseismology, the analysis of oscillations in a star's brightness that reveal information about its internal density structure. Different oscillation modes probe different depths within the star, much as different seismic waves probe different layers of the Earth's interior. By measuring the frequencies and amplitudes of Betelgeuse's pulsation modes and comparing them to the predictions of stellar evolution models, Joyce and her colleagues sought to determine which fusion stage the core was currently in. Their conclusions was that Betelgeuse is most likely in the early stages of core carbon burning. If this is correct, it places the star approximately 100,000 years from supernova. That is a long time by human standards, roughly 5,000 generations. It would mean that no one alive today, and no one alive for thousands of generations to come, would witness the explosion. It would be a problem for the far future, not our problem. However, not all researchers agree with this assessment, and the disagreements are not trivial. They go to the heart of how we understand the final stages of stellar evolution. To appreciate why the disagreements persist, it helps to understand what actually happens inside a red supergiant during its final years and centuries. The core of Betelgeuse is not a uniform ball of burning material. It is a stratified structure, a nested series of shells, each burning a different element at a different temperature and density. At the very center sits the ash of whatever fusion stage is currently active, surrounded by the actively burning shell, surrounded in turn by the ash and fuel of earlier stages. The entire structure is compressed under the immense gravitational weight of the star above it. The pressures and temperatures involved are beyond anything that exists naturally on Earth. During core carbon burning, the central temperature reaches roughly 600 to 800 million degrees Celsius. At these temperatures, carbon nuclei, each containing 6 protons and 6 neutrons, collide with enough energy to fuse into heavier elements, neon, sodium, and magnesium. The reactions release energy, but less energy per reaction than hydrogen or helium burning produced. The core must therefore burn faster to maintain the same outward pressure. Carbon burning in a star of Betelgeuse's mass lasts roughly 1,000 years, a period that seems long by human standards, but is vanishingly short compared to the millions of years of hydrogen burning that preceded it. When the carbon is exhausted, the core contracts once more. The temperature climbs past 1.2 billion degrees. At this point, something unusual happens. The neon nuclei, which were produced during carbon burning, begin to disintegrate. This process, called neon photodisintegration, involves high-energy photons stripping alpha particles from neon nuclei, which then fuse with other neon nuclei to produce oxygen and magnesium. The process is endothermic in its first step and exothermic in its second, but the net effect is a brief, intense burning phase that lasts approximately 1 year in a star of this mass. 1 year. After 1,000 years of carbon burning and millions of years of hydrogen burning, the neon phase is over in 12 months. Oxygen burning follows almost immediately. At temperatures above 2 billion degrees Celsius, oxygen nuclei fuse to produce silicon, sulfur, phosphorus, and other intermediate mass elements. This stage lasts a few months, perhaps 6 months to a year, depending on the stellar mass. The energy release is modest, but sufficient to briefly stabilize the core before the final act, and then comes silicon burning. At temperatures above 3 billion degrees Celsius, silicon nuclei undergo a complex network of reactions, adding alpha particles and protons step by step to build nuclei all the way up to iron and nickel. This is the final exothermic fusion process. Once the silicon is converted to iron, no further fusion can release energy. The core has built an iron ball at its center, and this iron ball is growing heavier with every passing hour. Silicon burning lasts approximately 1 day, perhaps less, and then the iron core reaches roughly 1.4 solar masses, a threshold called the Chandrasekhar limit, and the electron degeneracy pressure that had been helping to support it fails catastrophically. The core implodes. The collapse happens at approximately 70,000 kilometers per second, roughly 1/4 the speed of light. Within a fraction of a second, the core is compressed from a sphere roughly the size of Earth to a ball roughly 20 kilometers across. The density reaches that of an atomic nucleus, roughly 230 million tons per cubic centimeter. At this point, the strong nuclear force, which normally operates only within individual atomic nuclei, becomes the dominant force throughout the entire neutron star core. The collapse bounces. The rebounding material generates a shock wave that begins propagating outward through the star. But the shockwave alone is not enough. It stalls. The energy of the bounce is insufficient to overcome the gravitational pull of the enormous mass of stellar material still falling inward. For decades, this was one of the great unsolved problems in astrophysics. How does the shockwave revive and eventually blow the star apart? The answer, worked out through increasingly sophisticated computer simulations over the past 30 years, involves neutrinos. A collapsing core produces an enormous flood of neutrinos, roughly 10 to the 58 of them, carrying approximately 99% of the total gravitational energy released by the collapse. Most of these neutrinos escape immediately, passing through the overlying material as if it were not there, but a small fraction, less than 1%, are absorbed by the material just behind the stalled shockwave. This tiny fraction of the neutrino energy is sufficient to revive the shock, to push it outward with enough force to overcome gravity and tear the star apart. The entire process, from the moment the iron core begins to collapse to the moment the shock wave breaks through the stellar surface, takes roughly 3 hours for a star of Betelgeuse's size. 3 hours from the death of the core to the birth of the supernova. And during those 3 hours, the surface of the star shows nothing. No change in brightness, no change in color, no change in anything observable. The catastrophe is unfolding deep inside, hidden behind hundreds of millions of kilometers of stellar material, and the surface remains calm and unaware. A study published in 2023 by a team that included Sarafina Nances at the University of California, Berkeley, suggested that certain observational signatures of Betelgeuse are consistent with a star that may have already progressed beyond carbon burning. The surface activity that has been observed in recent years, the increasingly irregular pulsations, the massive ejections of material from the photosphere, the strange and unpredictable changes in brightness, these could be signs of a star in a later, more advanced stage of evolution than the carbon-burning models predict. If Betelgeuse has already begun neon burning, the timeline collapses from 100,000 years to perhaps a few thousand. If oxygen burning has begun, the timeline is measured in months. And if silicon has ignited in the core, the star has hours. But here is the problem. Both interpretations are consistent with the available observational data. The surface behavior of a star in late carbon burning and a star in early neon burning may look indistinguishable from the outside. The error bars in the models are enormous. The mass, the rotation rate, the internal mixing processes, the mass loss history, all of these parameters affect the predictions, and none of them can be directly measured with current technology. We are, in a very real and uncomfortable sense, guessing. It is educated guessing, informed by the best physics and the best observations that humanity has ever produced. But it is guessing nonetheless, and it gets worse. The mass of Betelgeuse itself remains stubbornly uncertain. For decades, the most commonly cited distance to Betelgeuse was roughly 650 light-years, based on parallax measurements from the European Space Agency's Hipparcos satellite, which operated in the early 1990s. At that distance, the observed luminosity and temperature of the star implied a mass of roughly 15 to 20 solar masses. But more recent analyses, including revised Hipparcos data and independent estimates using other techniques, have suggested the distance might be closer to 700 or even 724 light-years. This may seem like a minor correction, a change of 70 or 80 light-years out of 700. But the consequences are significant. A greater distance means a greater intrinsic luminosity, because the same apparent brightness from farther away requires the source to be inherently more luminous. A greater luminosity implies either a greater mass or a different evolutionary state, or both. The revised distance estimates have sent ripples through the community of researchers who model Betelgeuse, forcing them to reconsider assumptions about the star's mass, its age, its current evolutionary phase, and its remaining lifetime. Parameters that had been treated as settled for years were suddenly in play again. The mass matters because it determines the remnant. After the supernova, after the outer layers have been blown away and the core has collapsed, what remains depends critically on the mass of the original star and how much of that mass was lost during the star's lifetime through stellar winds. A star at the lower end of the mass range for Betelgeuse, around 12 to 15 solar masses, would most likely leave behind a neutron star, an object roughly 20 kilometers in diameter, but containing more mass than the Sun, with a density so extreme that a teaspoon of neutron star material would weigh roughly 6 billion tons. A star at the higher end, above roughly 20 to 25 solar masses, might produce a remnant too massive to be supported even by neutron degeneracy pressure, and the core would collapse further into a black hole. The distinction between a neutron star remnant and a black hole remnant is not academic. It affects the energy of the explosion, because a black hole formation event can be either more or less energetic than a neutron star formation event, depending on the dynamics of the collapse. It affects the quantity of neutrinos released. It affects the amount of heavy elements synthesized in the explosion and scattered into the interstellar medium, and it affects the long-term evolution of the surrounding region of space, because a black hole remnant and a neutron star remnant interact differently with any material that falls back after the explosion. Now, let us return to the Great Dimming, because it is central to understanding the current state of Betelgeuse and the reasons for the ongoing scientific debate. Between late 2019 and early 2020, Betelgeuse's brightness in visible light dropped to roughly 35 to 40% of its normal value at that phase of its pulsation cycle. This was not a subtle effect. It was the most dramatic dimming event recorded in the entire history of modern astronomical observation of this star. For comparison, the normal variability of Betelgeuse involves brightness changes of perhaps 20 to 30% over its roughly 400-day pulsation cycle. The Great Dimming was far deeper than this. It was also more rapid, occurring over a period of roughly 4 to 5 months, rather than the usual slow, cyclical fluctuation. Two competing hypotheses emerged almost immediately to explain the event. The first hypothesis proposed that Betelgeuse had ejected a large cloud of material from its surface, and this material, cooling as it moved away from the star, had condensed into dust grains that blocked a significant portion of the star's visible light from reaching Earth. The second hypothesis proposed that an unusually large convective cell, a massive bubble of hot plasma rising from deep within the star's interior, had cooled a significant portion of the visible surface, reducing the overall brightness without any intervening dust. The debate raged through 2020 and into 2021. Multiple research groups brought different data and different analyses to bear on the question. Observations from the Hubble Space Telescope, which had been monitoring Betelgeuse's ultraviolet emission before, during, and after the dimming, proved particularly valuable. So did observations from the Very Large Telescope in Chile, the Stellar Robotic Observatory in the Canary Islands, and a network of ground-based photometric stations that had been tracking Betelgeuse's brightness. By mid-2021, a consensus began to emerge, and the answer was both. Both hypotheses were correct, because both processes had occurred simultaneously. Betelgeuse had experienced a massive surface mass ejection, a colossal eruption of material from its photosphere that was unlike anything previously observed on any star. The ejected material, estimated to contain roughly twice the mass of the Moon, roughly 1.5 times 10 to the 23 kilograms, was launched outward from the surface at speeds of several hundred kilometers per second. As this material moved away from the star and cooled, it condensed into a cloud of dust grains that partially obscured the visible disk. At the same time, the eruption left behind a cooler, darker region on the stellar surface, further reducing the overall brightness. The combined effect of the dust cloud and the surface cooling produced the dramatic dimming that was observed. This surface mass ejection was not analogous to anything our Sun does. The Sun occasionally produces coronal mass ejections, eruptions of material from its outer atmosphere that send billions of tons of charged particles streaming through the solar system. These events can disrupt satellites, power grids, and communications on Earth, but the surface mass ejection from Betelgeuse was of an entirely different magnitude. Our Sun's largest coronal mass ejections involve perhaps 10 to 100 billion tons of material. Betelgeuse ejected roughly 400 billion times more material in a single event. Andrea Dupree of the Harvard Smithsonian Center for Astrophysics who led the analysis of the Hubble ultraviolet data, described the event as something that had never before been observed in the behavior of any normal star. It was, in her words, a truly novel event. The implications of this surface mass ejection extend far beyond explaining the Great Dimming. If Betelgeuse is capable of ejecting that much material in a single explosive event, it reveals something fundamental about the instability of its outer layers. The star is not simply pulsating in the calm, regular way that variable star theory might suggest. It is convulsing. The boundary between the star and the surrounding space, the photosphere, is not a clean, well-defined surface. It is a turbulent, chaotic, and occasionally violently eruptive transition zone where enormous masses of material can be flung outward with little warning. Some researchers have proposed that this kind of extreme surface activity could be linked to the deep internal processes occurring as the star progresses through its final fusion stages. As the core contracts and heats up between successive burning phases, the energy output increases and the outer layers of the star become increasingly unstable. The convective cells, the enormous columns of rising and falling plasma that transport heat from the interior to the surface, grow larger, more energetic, and more erratic. In a star like our Sun, convective cells are relatively small, each one roughly 1,000 kilometers across, producing the granulation pattern visible to the solar surface. In Betelgeuse, a single convective cell can span a significant fraction of the entire stellar disk. The turbulence is operating on a scale that is genuinely difficult to comprehend. Following the Great Dimming, Betelgeuse did not simply return to business as usual. Observations through 2021 and 2022 showed that the star's pulsation cycle had been disrupted. The normal roughly 400-day periodicity appeared to have been altered, with the star oscillating in unusual and unfamiliar patterns. Its brightness did not follow the expected curve. Instead, it showed irregular fluctuations that did not match any of the known pulsation modes. By late 2022 and into 2023, some researchers reported that the pulsation period appeared to be recovering, gradually settling back toward its normal value. But others noted that the star's average brightness remained elevated above its long-term historical average, as if the Great Dimming had triggered a lasting change in the star's equilibrium state. In June 2023, a study published in the Astrophysical Journal by Morgan McLeod of the Harvard-Smithsonian Center for Astrophysics and Andrea Dupree proposed a detailed mechanism for what had occurred. Their analysis suggested that the surface mass ejection had been so energetic, had removed so much material from the outer layers of the star, that it had physically disrupted the fundamental oscillation mode. The star's pulsation is analogous to a vibrating bell. Strike a bell gently, and it rings with a clean, characteristic tone determined by its shape and material. Strike it hard enough to dent it, and the tone changes. McLeod and Dupree argued, in essence, that the Great Dimming had dented the bell. The surface mass ejection had altered the structure of the outer layers enough to shift the star's resonant frequency. This matters enormously for our ability to determine the star's evolutionary state. If the pulsation data collected after 2020 are no longer directly comparable to the data collected before, then one of our primary diagnostic tools has been compromised. We need the pulsation period to constrain the models. We need it to estimate the average density. We need it to narrow down the range of possible internal structures. And now, at precisely the moment when the star is doing the most unusual things, the tool we rely on most heavily has become unreliable. There is another dimension to this problem that deserves attention. Betelgeuse is losing mass at a prodigious rate. Through its stellar wind, the continuous outflow of material from its surface, and through occasional violent events, like the Great Dimming ejection, Betelgeuse is shedding material into the surrounding space far faster than our Sun or any other modest star. Estimates of the mass loss rate vary, but most place it somewhere between 1 solar mass every 10,000 years and 1 solar mass every 100,000 years. Even the lower estimate is millions of times faster than the Sun's mass loss rate. Over the course of its lifetime, Betelgeuse may have lost several solar masses of material. material that now forms a vast multi-layered circumstellar envelope surrounding the star. Observations by the Herschel Space Observatory, a European Space Agency infrared telescope that operated from 2009 to 2013, revealed a bow shock in this circumstellar material. A bow shock forms when an object moves through a medium faster than the speed of sound in that medium, similar to the bow wave created by a ship moving through water. Betelgeuse is moving through the local interstellar medium at a speed of roughly 30 kilometers per second, and the material it has been shedding for millions of years has piled up in front of it, creating a visible shock front roughly half a light year ahead of the star. The existence of this bow shock tells us that Betelgeuse has been losing significant mass for a very long time, continuously seeding the space around it with stellar material. This ongoing mass loss affects everything. It affects the final mass of the core at the moment of collapse, which determines whether the remnant will be a neutron star or a black hole. It affects the energy budget of the supernova, because the explosion must push through the circumstellar envelope on its way outward, and the interaction between the shock wave and this pre-existing material can dramatically alter the appearance and brightness of the supernova. It affects the spectral signatures of the explosion, because when the blast wave collides with dense shells of previously ejected material, it produces characteristic emission lines that reveal the history of mass loss in the final millennia before the explosion. And it introduces yet another source of uncertainty into the models, because the mass loss rate itself is not constant. It varies with the star's pulsation phase, with the occurrence of surface mass ejections, like the one that caused the Great Dimming, and potentially with the internal evolutionary state, in ways that are not fully understood. In fact, the circumstellar environment of Betelgeuse is so rich and complex that it has become a field of study in its own right. Multiple shells and arcs of material have been detected at various distances from the star, each one recording a different episode of mass loss from a different epoch. The innermost material closest to the star was ejected most recently and reveals the current mass loss behavior. The outermost material, at distances of several light years, was ejected millions of years ago and reveals the mass loss history during earlier phases of the star's evolution. By studying these shells, researchers can reconstruct a timeline of mass loss that extends back through a significant portion of Betelgeuse's existence as a red supergiant. But interpreting this timeline requires assumptions about the velocity of the ejected material, the density of the surrounding interstellar medium, and the geometry of the ejection events, all of which introduce additional uncertainties. Something is wrong with our assumptions. That is, the uncomfortable, recurring theme in the study of Betelgeuse. Every time a new observation is made, every time a more sophisticated model is run, the answer to the fundamental question, when will it explode, shifts. The models do not converge. The observations are ambiguous. The parameters that matter most, the mass, the distance, the evolutionary state, the mass loss history, all carry uncertainties large enough to change the answer from not for a very long time to possibly soon and back again. We are not dealing with a well-characterized problem that is gradually being solved. We are dealing with a deeply uncertain situation that resists resolution. What we can say with confidence is this: Betelgeuse is a star on the edge. It has entered the final stages of its evolution. The processes occurring in its core are accelerating, each stage burning faster and more desperately than the last. The surface is increasingly turbulent and unstable, capable of eruptions that dwarf anything in our solar system by orders of magnitude. The pulsation has been disrupted. The mass loss continues. The clock is ticking, even if we cannot read it clearly. Every observation brings us closer to understanding. But understanding is not prediction, and prediction is what every headline, every social media post, every conversation about Betelgeuse ultimately demands. Will it explode in our lifetime? The honest answer is that we do not know. The honest answer is that we may never know until the moment it happens. We can narrow the range, we can update the models, we can gather more data with more powerful instruments, but the fundamental opacity of stellar interiors remains. We cannot see the core, we cannot watch the iron accumulate, We cannot measure the temperature at the center of the star. We can only watch the surface, read the clues it offers, and try to infer what is happening hundreds of millions of kilometers below. And there is a sobering historical precedent for our limitations. In 1987, supernova 1987A was observed in the Large Magellanic Cloud. It was the first supernova visible to the naked eye since 1604, and the star that exploded, Sanjulak -69 degrees 202, was not a red supergiant. It was a blue supergiant. The models had predicted that core collapse supernovae should occur primarily in red supergiants. The blue supergiant progenitor was a surprise, and it forced a major revision of stellar evolution theory. The lesson was clear. Our models, however sophisticated, are not infallible. The universe is perfectly capable of surprising us, and the next surprise could come from Betelgeuse. But here is what makes this truly terrifying. When Betelgeuse does finally go supernova, there will be almost no warning. Not for us. The core collapse, the actual moment of death when the iron core exceeds the Chandrasekhar limit and the electron degeneracy pressure fails, will occur in less than 1 second. The shock wave generated by the bounce of the collapsing core will take several hours to propagate outward through the star's massive envelope and reach the surface. The neutrino burst from the collapse will arrive at Earth roughly 700 years later, traveling at the speed of light. The visible light from the supernova will follow minutes to hours after the neutrinos. And before the neutrinos arrive, before the light arrives, there will be silence. 700 years of silence. The star's core may have already collapsed. The shock wave may already be tearing through the outer layers, and we will not know until the neutrinos hit our detectors and the light reaches our eyes. We are watching a star that could already be dead, and the message of its death could be hurtling toward us, right now, at the speed of light, and there is absolutely nothing we can do except wait. Scientists have not been passive in the face of this uncertainty. Over the past several decades, multiple approaches have been employed to try to determine the evolutionary state of Betelgeuse and predict, or at least constrain, the timing of its eventual supernova. Each approach has yielded valuable insights. Each has also encountered significant limitations. The story of these attempts is itself a story about the boundaries of human knowledge and the humbling difficulty of understanding a single star from a distance of 700 light-years. The first and most fundamental approach has been stellar evolution modeling. This is the method of building detailed computer simulations that track the life of a star from its birth on the main sequence, through each successive fusion stage, all the way to its death as a supernova. These models take as input the initial mass, chemical composition, rotation rate, and magnetic field strength of the star, and then evolve it forward in time, calculating at each step the nuclear reactions occurring in the core, the energy transport through the stellar interior via radiation and convection, the changes in size, temperature, and luminosity, and the mass lost through stellar winds. The output is a predicted evolutionary track, a path through a diagram called the Hertzsprung-Russell diagram that maps surface temperature against luminosity. By comparing Betelgeuse's observed temperature and luminosity to the predicted evolutionary tracks, researchers can estimate where the star currently sits in its life cycle. The models are genuinely sophisticated. They incorporate decades of experimental nuclear physics data, measuring the rates of dozens of individual nuclear reactions at the temperatures and densities relevant to stellar interiors. They include detailed equations of state that describe how matter behaves at the extreme pressures and temperatures found in stellar cores. They implement complex treatments of convection, the turbulent mixing of material that transports heat from the core to the surface, which remains one of the most challenging problems in all of theoretical astrophysics. They account for rotation, which can affect the internal mixing, and therefore the rate at which fuel is consumed. And they include prescriptions for mass loss, the continuous shedding of material from the stellar surface through winds and eruptions. Several major computational codes are used for this work. The MESA code, which stands for Modules for Experiments in Stellar Astrophysics, was developed at the University of California, Santa Barbara, and has become one of the most widely used tools in the field. It is open source, meaning that any researcher in the world can download it, modify it, and use it for their own simulations. The code has been continuously developed and improved since its first release in 2011, with each new version incorporating updated nuclear reaction rates, improved treatments of convection and mass loss, and better numerical methods. The Geneva Stellar Evolution Code, developed by a team at the University of Geneva in Switzerland, led by Andromeda and Georges Ménet, has been particularly influential in studying the effects of rotation on massive star evolution. Their work showed that rotation can dramatically alter the internal mixing profile of a massive star, bringing fresh hydrogen fuel into the core and extending the main sequence lifetime, while also affecting the subsequent evolution through heavier burning stages. The Kepler code, developed by Stan Worsley and his collaborators at the University of California, Santa Cruz, specializes in following massive stars all the way through core collapse and the supernova explosion itself, making it particularly valuable for predicting the properties of the supernova and the nature of the compact remnant. These codes represent some of the most sophisticated computational tools in all of astrophysics. They solve coupled differential equations describing nuclear burning, energy transport, gravitational contraction, and mass loss, evolving a virtual star through millions of years of history, one tiny map at a time. A single complete simulation of a massive star from the main sequence to core collapse can require millions of individual test-type pumps and generate terabytes of output data. The physical detail captured in these simulations is extraordinary, and yet the results are only as reliable as the inputs that drive them. Each code takes a slightly different approach to the underlying physics, uses slightly different numerical methods, and employs slightly different prescriptions for the processes that are not yet fully understood from first principles, particularly convection and mass loss. The differences are usually small, but in a problem as sensitive as predicting the remaining lifetime of Betelgeuse, small differences in the models can translate into large differences in the conclusions. But the models have a fundamental problem. They are exquisitely sensitive to inputs that we cannot directly measure. The initial mass of Betelgeuse, meaning the mass it had when it first formed and settled onto the main sequence roughly 8 to 10 million years ago, is not known with precision. Current estimates range from roughly 12 to over 20 solar masses, depending on the assumed distance, the assumed mass loss history, and the modeling framework used. A difference of just 2 solar masses in the initial mass can shift the predicted position on the Hertzsprung-Russell diagram by a noticeable amount, which in turn can shift the estimated remaining lifetime by tens of thousands of years. The rotation rate is similarly uncertain. We know that Betelgeuse rotates because observations have detected a rotational broadening of its spectral lines. But the current rotation rate of the extended red supergiant envelope is not the same as the rotation rate the star had when it was a compact, main sequence object. As the star expanded, conservation of angular momentum dictated that the surface rotation rate decreased, but the internal rotation profile, how fast different layers of the star spin relative to one another, depends on complex angular momentum transport processes that are not well understood. And the rotation rate matters, because rotation drives internal mixing, which affects how much fuel is available at each stage and how long each stage lasts. The numbers are striking. Run the same stellar evolution code with the same initial composition, but vary the initial mass from 14 to 18 solar masses, and the predicted remaining lifetime at Betelgeuse's current position on the Hertzsprung-Russell diagram can change from roughly 60,000 years to over 150,000 years. Vary the rotation rate, and the spread widens further. Add uncertainty in the mass loss prescription, and the range becomes even broader. The models are mathematically precise in the sense that each individual simulation produces an exact number, but the range of plausible inputs produces a range of outputs so wide that the models cannot, by themselves, answer the question of when Betelgeuse will explode. They give us exact answers to questions whose inputs are uncertain. The second major approach has been asteroseismology, the study of stellar oscillations. just as geologists use seismic waves from earthquakes to probe the interior structure of the Earth, revealing the layers of the crust, mantle, and core. Astronomers can use oscillations in a star's brightness to probe its interior structure. The principle is straightforward. When a star pulsates, it rings like a bell. Different oscillation modes, different patterns of expansion and contraction, probe different depths within the star. The fundamental mode, in which the entire star expands and contracts uniformly, is sensitive to the average density of the star. Higher order modes, in which different parts of the star move in opposite directions, probe the density and composition at specific depths. For sun-like stars and red giants, astroseismology has been spectacularly successful. The Kepler Space Telescope, which observed roughly 150,000 stars with extraordinary photometric precision from 2009 to 2018, revolutionized our understanding of stellar interiors by measuring oscillation frequencies for thousands of red giant stars. These measurements allowed researchers to determine not only the average density of each star, but also, through the detection of mixed modes that couple pressure oscillations in the envelope with gravity oscillations in the core, to determine the size and composition of the stellar core. For the first time, astronomers could effectively peer inside stars and determine whether they were burning hydrogen or helium in their cores, a distinction that was previously accessible only through theoretical models. The revolution was so profound that it earned the nickname the Golden Age of astroseismology. Thousands of red giants were characterized with a precision that would have been unimaginable just 20 years earlier. Core rotation rates were measured. Internal mixing processes were constrained. The ages of stars were determined with percent-level accuracy, all from the careful analysis of tiny rhythmic fluctuations in brightness. But Betelgeuse is not a red giant, it is a red supergiant, and red supergiants present a fundamentally more challenging target for astroseismology. Their pulsation periods are much longer, hundreds of days, rather than hours or minutes, which means that observing a single complete pulsation cycle requires months of continuous monitoring. Accumulating enough cycles to perform a detailed frequency analysis requires years, sometimes decades. Their pulsations are also considerably less regular than those of red giants, affected by the enormous convective cells that dominate their surfaces, and by the complex, multi-shell burning structure of their interiors. The turbulence on the surface of a red supergiant acts as a source of noise that can mask or distort the oscillation signal, and the theoretical models of red supergiant pulsation are less mature and less well-tested than those for smaller stars, because the extreme size, very low average density, and violently turbulent convection of these stars make the mathematical treatment of oscillations considerably more difficult. The pulsation of a red supergiant is not a clean, bell-like ringing. It is more like trying to detect the fundamental tone of a drum being played in a thunderstorm. Betelgeuse oscillates with a dominant period of roughly 400 days, corresponding to the fundamental radial mode in which the entire star expands and contracts like a slowly breathing lung. There is also evidence for a longer period variation of roughly 2,100 days, or approximately 5.8 years, which may correspond to a higher order pulsation mode, or to a completely different physical mechanism. And there are shorter timescale variations, on the order of weeks to months, that may be related to the convective activity on the stellar surface. Meredith Joyce's 2020 study used the observed pulsation period, combined with stellar evolution models from the MESAR code, to constrain Betelgeuse's evolutionary state. The reasoning was elegant. The fundamental pulsation period of a star depends primarily on its average density, which in turn depends on its mass and radius. If you know the period, and you have independent constraints on either the mass or the radius, you can work backward to estimate the average density, and from there, the internal structure. By running a grid of stellar evolution models with different initial masses and comparing the predicted periods to the observed period, Joyce and her team identified the models that best matched the data. Their conclusion was that Betelgeuse is currently in the early stages of core carbon burning. with an estimated remaining lifetime of roughly 100,000 years. This was the most specific constraint on Betelgeuse's evolutionary state that had been published to date. It was widely reported in both scientific and popular media, and it provided a degree of reassurance. 100,000 years is a long time, long enough to be someone else's problem. Long enough that the explosion of Betelgeuse could be filed away as an inevitability of the distant future rather than a present concern. This was a significant and carefully argued result, produced by a team with deep expertise in both astroseismology and stellar evolution. But it depended on assumptions. It assumed that the pulsation theory used was applicable to a red supergiant of Betelgeuse's extreme size and luminosity. It assumed that the observed period was the fundamental mode and not a higher harmonic or a non-radial mode. It assumed a particular distance, a particular mass loss prescription, and a particular treatment of convection in the stellar evolution models. Change any of these assumptions, and the conclusion could shift. And then the Great Dimming happened. And the Great Dimming may have broken the bell. If MacLeod and Dupree are correct that the surface mass ejection disrupted the fundamental pulsation mode of the star, then the asteroseismic analysis is in trouble. The period measured before the Great Dimming and the period measured after may not refer to the same physical oscillation. The star may be ringing with a different frequency, one that does not correspond to the same average density, and therefore does not provide the same constraints on the internal structure. Joyce herself acknowledged this issue in subsequent work, noting that ongoing monitoring would be needed to determine whether the pulsation has returned to its pre-dimming state. The third approach has been direct imaging and interferometry. Betelgeuse is one of the very few stars whose surface can be directly resolved by existing telescope technology. Its angular diameter on the sky is roughly 42 to 44 milliarcseconds, which is tiny in absolute terms but enormous by stellar standards. For comparison, a milliarcsecond is roughly the angle subtended by a quarter placed on the ground in Los Angeles and viewed from New York. It takes extremely high-resolution instruments to resolve angles this small. The technique most commonly used is optical interferometry, in which the light from two or more separated telescopes is combined to produce an image with an angular resolution far higher than any single telescope could achieve. The Very Large Telescope Interferometer at the European Southern Observatory's Paranal facility in Chile combines the light from four 8.2-meter telescopes with baselines of up to 130 meters. The Chara Array at Mount Wilson Observatory in California uses six 1-meter telescopes with baselines of up to 330 meters, achieving even higher angular resolution. Both facilities have been used extensively to study Betelgeuse. The images that have emerged from these observations are extraordinary. They reveal a surface that is nothing like the smooth, uniform disk one might naively expect. Instead, the surface of Betelgeuse is dominated by a handful of enormous convective cells, bright and dark patches that span significant fractions of the stellar disk and that change position, shape, and brightness over periods of weeks to months. The surface is in constant motion, roiling and churning, like a pot of thick soup heated from below, but on a scale that defies easy comparison. A single bright convective cell on Betelgeuse can be several 100 million kilometers across, larger than the distance between the Earth and the Sun. In early 2020, just as the Great Dimming was reaching its deepest point, the VLT gravity instrument captured stunning images showing that the dimming was concentrated in the southern hemisphere of the stellar disk. The northern hemisphere appeared relatively unchanged, while the southern portion was significantly darker. This asymmetric dimming pattern was a crucial piece of evidence in piecing together what had happened. It was consistent with a dust cloud that was blocking part of the star's visible surface, a cloud positioned between us and the southern half of the disk. Later observations confirmed this interpretation and tracked the subsequent clearing of the dust cloud over the following months as the ejected material dispersed. The gravity instrument continued monitoring Betelgeuse through 2021, 2022, and beyond. The images showed a stellar surface in a state of ongoing turmoil, with new bright spots appearing and fading, the overall shape of the star fluctuating slightly. and the brightness distribution shifting from month to month. In 2022, analysis of VLTI data combined with spectropolarimetric observations from the Naval Instrument at the Pic du Midi Observatory in France provided evidence that the surface mass ejection associated with the Great Dimming may have been related to a large convective upwelling. The picture that emerged was of a massive plume of hot material rising from deep within the star, breaking through the surface and launching a blob of material into the surrounding space with enough energy to escape the star's gravitational pull. There is an additional complication that makes direct imaging difficult. Betelgeuse is surrounded by a complex, extended atmosphere that is partially transparent at some wavelengths and opaque at others. At infrared wavelengths, the star appears larger than it does in visible light, because the infrared radiation probes deeper into the extended atmosphere. At millimeter wavelengths, as observed by ALMA, the star appears larger still, because the cooler, more extended layers of the chromosphere emit at these wavelengths. Defining the surface of Betelgeuse is not as simple as it might seem. The star does not have a sharp edge. It has a gradual, fuzzy transition from dense, hot photospheric material to thin, cool circumstellar material, and the apparent size depends on the wavelength at which you observe. ALMA observations from 2017 and 2020 provided some of the most detailed views of Betelgeuse's extended atmosphere. These observations revealed hot gas at temperatures of several thousand degrees, extending well beyond the visible photosphere, as well as cooler material at distances of several stellar radii that appeared to be in the process of condensing into dust grains. The observations showed that Betelgeuse is continuously producing dust, not just during dramatic events like the Great Dimming. The steady dust production contributes to the circumstellar envelope and represents an ongoing mechanism of mass loss that supplements the general stellar wind. These observations have provided critical constraints on the size and temperature of Betelgeuse, both of which are essential inputs to the evolutionary models. But they have also revealed a level of complexity that the models struggle to reproduce. Three-dimensional simulations of red supergiant convection, such as those produced by the CO5 bold code developed by Bernd Freytag and collaborators at Uppsala University in Sweden, do show large convective cells consistent with the observations. But these simulations are computationally extremely expensive, requiring months of computing time on some of the world's largest supercomputers to simulate just a few years of stellar time. They typically cover only a few pulsation cycles, far less than the thousands of cycles needed to track the long-term evolution of the star. Bridging the gap between the short-term, three-dimensional convection simulations and the long-term, one-dimensional evolution models remains one of the outstanding challenges in stellar astrophysics. It is a problem not just for understanding Betelgeuse, but for understanding all red supergiants and, by extension, all core collapse supernovae. The fourth approach has been neutrino monitoring, and this represents perhaps the most tantalizing intersection of particle physics and astronomy. To understand why neutrino detection matters so much for Betelgeuse, you need to appreciate the role that neutrinos play in the death of a massive star. When a massive star's core collapses, the vast majority of the gravitational energy released, roughly 3 times 10 to the 46 joules, a number so large it has no meaningful intuitive analog, is carried away by neutrinos. These are electrically neutral, nearly massless particles that interact with matter only through the weak nuclear force and gravity. Their interaction cross-section is so extraordinarily small that a typical neutrino could pass through a wall of solid lead 1 light-year thick, roughly 9.5 trillion kilometers, without being absorbed. They are, for all practical purposes, invisible, and yet, during the core collapse of a massive star, they carry away roughly 99% of the total energy. The light that we see from a supernova, the spectacular visual display that outshines a galaxies, represents only about 1% of the energy released. The rest leaves as neutrinos. When the core of Betelgeuse collapses, it will produce roughly 10 to the 58 neutrinos in a burst lasting approximately 10 to 15 seconds. That is a number with 58 zeros after it. Almost all of these neutrinos will pass through the overlying stellar material completely unimpeded and escape into space at nearly the speed of light. They will stream outward in all directions, passing through everything in their path. A small but detectable fraction of this flood will, 700 years later, reach Earth. At Earth, this neutrino burst would arrive several hours before the optical supernova becomes visible. This is because the neutrinos are produced in the core collapse itself, which occurs deep inside the star, and they escape almost immediately, passing through the stellar envelope as if it were not there. The light from the supernova, by contrast, is produced only when the shock wave from the core collapse finally reaches the stellar surface and blows the outer layers apart, a process that takes several hours for a star as enormous as Betelgeuse. This time delay between the neutrino arrival and the optical brightening provides a precious window of advance warning. Current neutrino detectors would be more than capable of detecting this signal. The Super Kamiokande detector in Japan, located roughly 1,000 meters underground in the Mozumi mine, consists of a cylindrical tank containing 50,000 tons of ultra-pure water, instrumented with roughly 11,200 photomultiplier tubes that can detect the faint flashes of Cherenkov radiation produced when a neutrino interacts with a water molecule. For a supernova at the distance of Betelgeuse, Super Kamiokande would register roughly 7,000 to 10,000 neutrino events over a period of approximately 10 seconds. This would be an overwhelming, unmistakable signal, unlike anything the detector experiences during normal operation. The IceCube Neutrino Observatory at the South Pole, which uses an entire cubic kilometer of Antarctic ice as its detection medium, instrumented with over 5,000 optical sensors, frozen into the ice at depths between 1,450 and 2,450 meters, would see an equally dramatic signal. Rather than detecting individual neutrino interactions, IceCube would observe a sudden, massive increase in its background count rate as the neutrino flood from the supernova raised the light level throughout the entire detector simultaneously. Other detectors would contribute as well. The Baksan Neutrino Observatory in Russia, the Borexino detector in Italy, the Daya Bay and Juno detectors in China, and the planned Hyper Kamiokande detector in Japan, which at 260,000 tons will be roughly 5 times the volume of Super Kamiokande, would all register the signal. Taken together, these detectors would provide detailed information about the energy spectrum, the time profile, and the flavor composition of the neutrino burst, which would in turn reveal the dynamics of the core collapse, the formation of the neutron star, and the mechanism by which the shock wave is revived and the explosion is launched. The Supernova Early Warning System, known as SNEUS, links these detectors and others in a real-time alert network. If 2 or more detectors register a coincident burst of neutrinos consistent with a core collapse supernova within a narrow time window, the system automatically generates an alert and distributes it to astronomical observatories around the world. The alert would trigger immediate observations across all wavelengths, ensuring that the first moments of the visible supernova are captured by every available instrument. The original SNEUS system was established in 2005. An upgraded version, SNEUS 2.0, was deployed in 2021, incorporating additional detectors, improved triangulation algorithms that can estimate the direction of the supernova from the relative timing of neutrino arrivals at different detectors, and faster communication protocols designed to get the alert out within seconds of the trigger. But here is the limitation that no amount of detector upgrades can overcome. Neutrino detection is reactive, not predictive. It can tell us that a supernova has begun. It cannot tell us that one is about to begin. The neutrino burst arrives only after the core has already collapsed. By the time our detectors ring, the star is already dead. Its core has already been crushed into a neutron star or a black hole. The warning is measured in hours, perhaps a day at most, before the visible supernova appears. And before that warning comes, before the neutrinos arrive, there is nothing. No signal, no precursor, no observable change in the star's behavior that we can currently detect from interstellar distances. This means that despite our impressive global network of neutrino detectors and our automated alert systems, we are essentially waiting in darkness for the bell to ring. We will have hours of warning before the light show begins, but we will have no warning at all that the core is about to collapse. And for a star 700 light-years away, even the hours of warning provided by the neutrino burst are, in one sense, an illusion. The core collapse that produced those neutrinos actually occurred roughly 700 years before the neutrinos reached us. We are not predicting the future. We are receiving news of the distant past, delivered at the speed of light. The fifth approach, and the most recently developed, is gravitational wave astronomy. According to Einstein's general theory of relativity, published in 1915, any asymmetric acceleration of mass produces ripples in the fabric of spacetime itself. These ripples, called gravitational waves, propagate outward from their source at the speed of light, stretching and compressing space as they pass. They carry information about the dynamics and geometry of the source, encoded in their frequency, amplitude, and polarization. The existence of gravitational waves was predicted by Einstein, but not directly confirmed until 2015, when the LIGO detectors in Hanford, Washington, and Livingston, Louisiana, simultaneously detected the signal from two merging black holes, roughly 1.3 billion light-years away. That detection, announced in February 2016, opened an entirely new window on the universe, a way of observing cosmic events that produce no detectable electromagnetic radiation. The LIGO detectors, together with the Virgo detector near Pisa in Italy and the Kagra detector in Kamioka, Japan, form a global network of gravitational wave observatories. Since the first detection, they have observed gravitational waves from dozens of binary black hole mergers, several binary neutron star mergers, and at least one mixed neutron star black hole merger. The signals from compact binary mergers are relatively clean and well understood because the physics of two orbiting compact objects gradually spiraling inward is governed by the well-tested equations of general relativity. Templates of expected signals can be pre-computed and compared against the observed data, allowing detections with high confidence. The gravitational wave signal from a core collapse supernova is an entirely different beast. The dynamics of the collapse are far more complex than a clean binary in-spiral. The collapsing core is not spherically symmetric. It is subject to various hydrodynamic instabilities. Convective plumes develop in the hot, dense proto-neutron star. The standing accretion shock ahead of the proto-neutron star undergoes a sloshing instability called the standing accretion shock instability, or SASI. If the proto-neutron star is born rotating rapidly, it may develop a rotational instability that produces a strong, quasi-periodic gravitational wave signal. All of these processes contribute to a gravitational wave signature that is expected to be rich in information but complicated in structure. At the distance of Betelgeuse, roughly 700 light-years, the gravitational wave signal from the supernova would be relatively strong compared to the signals from extragalactic compact binary mergers that LIGO has detected so far. Current estimates suggest that the signal should be detectable by the existing LIGO-Virgo-Kagra network, though the signal-to-noise ratio would depend on the orientation of the source, the details of the collapse dynamics, and the specific detector sensitivity at the frequencies where the supernova signal peaks, which is expected to be in the range of roughly 100 to 1000 Hz. The real revolution would come with next-generation gravitational wave detectors. The Einstein telescope, proposed for construction in Europe, would be a triangular underground detector with arms roughly 10 kilometers long, far larger than the current 4-kilometer LIGO arms. Cosmic Explorer, proposed for the United States, would have arms roughly 40 kilometers in length. These detectors would be roughly 10 times more sensitive than the current generation, which translates to a factor of roughly 1,000 in the volume of space they can survey. For a galactic supernova at the distance of Betelgeuse, the signal-to-noise ratio would be enormous, potentially allowing researchers to reconstruct the dynamics of the core collapse, the bounce, the shock revival, and the neutron star formation in remarkable detail. The gravitational wave would be synchronized with the neutrino signal and the electromagnetic observations, providing a multi-messenger dataset of unprecedented richness. But again, and this is the recurring theme: gravitational wave detection is reactive. It tells us about a collapse that has occurred. It cannot predict one. The gravitational waves from a Betelgeuse supernova would arrive at Earth simultaneously with the neutrino burst. Since both travel at the speed of light, we would gain no additional warning time. We would gain additional information of immense scientific value, but we would not gain foresight. There is a sixth consideration that does not fit neatly into any of the previous 5 categories, but that has attracted increasing attention in recent years. This is the search for pre-supernova neutrinos. Theoretical calculations suggest that during the final days and hours of a massive star's life, as the silicon burning phase progresses and the iron core grows, the neutrino emission from the core increases significantly above the baseline level that exists during earlier burning stages. These pre-supernova neutrinos are produced by a process called thermal neutrino emission, in which extremely high temperatures in the core create neutrino-antineutrino pairs that escape the star. The energy of these pre-supernova neutrinos is lower than the energy of the neutrinos produced during the actual core collapse. They are also far fewer in number. But at the distance of Betelgeuse, 700 light-years, some calculations suggest that the pre-supernova neutrino flux might be detectable by next-generation neutrino detectors in the final hours or days before the collapse. If so, this could extend the warning time from hours to perhaps a day or more. The Juno detector being built in China, which will contain 20,000 tons of liquid scintillator, has been specifically designed with sensitivity to low-energy neutrinos that could include pre-supernova signals from nearby massive stars. Hyperkamiokande, with its vastly larger volume, would also contribute to this effort. However, the theoretical predictions carry significant uncertainties, and no pre-supernova neutrino signal has ever been detected from any star. The concept remains speculative, and even the most optimistic scenarios provide only hours to days of additional warning, not the years or decades that would be needed for true prediction. Each of these approaches, stellar evolution modeling, astroseismology, direct imaging, neutrino detection, gravitational wave detection, and the speculative search for pre-supernova neutrinos, provides a different and valuable perspective on the problem. None of them, alone or in combination, can currently tell us when Betelgeuse will explode. The models give us a range of possibilities, too broad to be useful for scheduling. The observations give us snapshots of a star in ongoing turmoil, changing faster than some of the models predict. The detectors give us the promise of a warning that will come only at the very end, measured in hours rather than years, and delivered 7 centuries after the event itself. We are left in a position that is profoundly unusual in modern science. We know with near certainty that a specific, named, visible, well-studied, and culturally significant object in the night sky will undergo one of the most energetic events in the known universe. We know the physics of how it will happen. We know what we will see, hear, and measure when it does. We have instruments deployed around the world and in orbit waiting for it. International collaborations have been organized for the sole purpose of being ready when it comes. But we cannot predict when. The uncertainty is not gradually shrinking toward a precise answer. It remains stubbornly, frustratingly broad, spanning 5 orders of magnitude, from years to hundreds of thousands of years. And closing that gap may require theoretical and observational breakthroughs that have not yet been conceived, technologies that have not yet been invented, and a deeper understanding of stellar interiors than we currently possess. There is a kind of humility embedded in this situation that is worth pausing to appreciate. For all our telescopes and interferometers, our neutrino detectors buried deep underground, our gravitational wave observatories stretching across kilometers of landscape, our supercomputers running for months on end, we are watching Betelgeuse in much the same spirit that ancient civilizations watched it, with attention, with wonder, with curiosity, and with no real knowledge of what happens next, or when. We know vastly more about the mechanisms. We understand the physics in far greater detail than any previous generation of humans. But the fundamental question, the one that matters most to anyone looking up at the sky on a clear winter night, remains as unanswered today as it was 1,000 years ago. When will it happen? The universe is under no obligation to answer, and so far it has chosen silence. There is a deeper truth beneath all the observational uncertainty, all the modeling debates, all the competing theories and revised distance estimates and disrupted pulsation modes. And it is this. Betelgeuse is not unique. It is not even unusual. It is simply the nearest and most visible example of a process that is happening constantly, everywhere in the universe, and that has been happening for nearly as long as the universe itself has existed. There are hundreds of red-sode supergiants in our galaxy alone. Each one is a ticking clock, each one burning through its fuel reserves on an accelerating schedule, each one destined for the same catastrophic end. Antares, in the constellation Scorpius, is another red supergiant roughly similar in size and mass to Betelgeuse, sitting at a distance of roughly 550 light-years. Mu Tephei, sometimes called Herschel's garnet star for its deep red colour, is a red supergiant even larger than Betelgeuse, one of the largest stars known in our galaxy, at a distance of roughly 2,400 light-years. VY Canis Majoris, at a distance of roughly 3,900 light-years, is a red hypergiant so extreme in its size and mass loss rate that it exists at the very edge of what stellar structure theory can explain. Each of these stars will eventually go supernova. Each one is in some stage of the same decline that Betelgeuse is experiencing. But Betelgeuse is the closest, the brightest, and the most thoroughly studied. It is the one we have chosen to watch most carefully, and it may well be the one that gives us the first ringside view of a core collapse supernova in the age of modern astrophysics. In our own Milky Way galaxy, a supernova occurs roughly once every 50 years on average, based on observations of similar galaxies and on indirect evidence from the abundances of radioactive isotopes produced in supernovae. Most of these go unobserved, hidden behind the dense clouds of dust and gas that fill the galactic plane and block visible light from reaching us. The last supernova observed in our galaxy with the naked eye was Kepler's supernova in 1604. Before that, Tycho's supernova in 1572, and before that, a supernova recorded by Chinese and Arabic astronomers in 1054, the remnant of which is now the famous Crab Nebula in the constellation Taurus. The gap of over 400 years since the last visible galactic supernova is in some sense a statistical anomaly. We are overdue. The galaxy has almost certainly hosted supernovae during this interval that were simply hidden from our view by interstellar dust. When Betelgeuse does go supernova, it will be the closest such event observed in the era of modern astronomy by an enormous margin. The most recent supernova studied in detail was SN 1987A, which occurred in the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way at a distance of approximately 168,000 light-years. It was the first supernova visible to the naked eye since Kepler's in 1604, and it was a landmark event in astronomy. It provided the first detection of neutrinos from a supernova, with a total of 25 neutrinos recorded by 3 detectors worldwide. It confirmed the basic theoretical picture of core collapse, and it provided decades of follow-up observations as the expanding debris cloud illuminated the surrounding interstellar medium. But Betelgeuse is roughly 240 times closer than SN 1987A. Let that sink in. The inverse square law tells us that the apparent brightness of a source scales inversely with the square of the distance. If a Betelgeuse supernova had the same intrinsic luminosity as SN 1987A, it would appear roughly 57,000 times brighter from Earth. In practice, the two supernovae would not be identical, because the progenitor stars are different types with different properties, but the order of magnitude comparison is valid. A Betelgeuse supernova would be vastly, overwhelmingly brighter in our sky than anything in living memory or in the last several centuries of astronomical history. The peak apparent magnitude would reach roughly -12 to -13. For context, the full moon has an apparent magnitude of roughly -12.7. Venus, the brightest planet, reaches a maximum of roughly -4.6. Sirius, the brightest star in the night sky, has an apparent magnitude of roughly -1.46. A Betelgeuse supernova would be roughly 15,000 times brighter than Sirius. It would be visible in broad daylight. At night, it would cast visible shadows on the ground. It would be, by a wide margin, the brightest object in the night sky after the moon. The entire constellation of Orion would be transformed. The familiar pattern of bright stars that has been recognized by every human culture for thousands of years would be disrupted by an overwhelmingly bright point of light on its upper left shoulder. The carefully balanced arrangement of Betelgeuse, Rigel, Bellatrix, Saiph, and the three belt stars would be thrown into a new visual configuration, dominated by a single, piercing light that would make the other stars in the constellation difficult to see by comparison. The supernova would remain visible to the naked eye for roughly 1 to 2 years after the initial peak. The brightness would fade gradually as the expanding debris cloud, moving outward at speeds of several thousand kilometers per second, cooled and dispersed. The initial peak would last several weeks, during which the supernova would remain brighter than any other star in the sky. Over the following months, it would dim from its extraordinary peak but remain easily visible, fading slowly through the range of brightness occupied by the brightest stars. After a year or two, it would drop below naked eye visibility, though it would remain observable through telescopes for decades, centuries, and millennia as the expanding supernova remnant continued to evolve. This is not science fiction. This is straightforward physics applied to a well-measured star at a known distance. Every calculation, every model, every observation converges on the same basic picture. This will happen. The only variable is the timing. But what about the danger? This is the question that surfaces most often in public discussions of Betelgeuse, and it is worth addressing directly and thoroughly. At a distance of 700 light-years, a Betelgeuse supernova would pose no significant threat to life on Earth. The distance is simply too great. The most dangerous effects of a supernova, the intense burst of ultraviolet and X-ray radiation, the flood of energetic cosmic ray particles, and the physical blast wave of expanding material all diminish with the square of the distance. At 700 light-years, the radiation flux from the supernova at Earth's orbit would be negligible compared to the normal radiation environment that the planet experiences from the Sun and from background cosmic rays. There has been some discussion in the scientific literature about whether the neutrino flux from a supernova at Betelgeuse's distance could affect Earth's ozone layer. The mechanism would be indirect. A sufficiently intense flux of cosmic ray particles, accelerated by the supernova shockwave over subsequent centuries, could potentially catalyze the destruction of ozone molecules in the upper atmosphere, increasing the amount of ultraviolet radiation reaching the surface. However, the most thorough analyses of this scenario, including detailed atmospheric modeling by Adrian Melott at the University of Kansas and astrophysical calculations by Mark Deal at the Max Planck Institute, suggest that a supernova would need to occur within roughly 30 to 50 light-years of Earth to cause significant ozone depletion. Betelgeuse is more than 14 times farther away than this threshold. The ozone layer would be unaffected. The blast wave of material from the supernova, traveling at several thousand kilometers per second, would take roughly 2 million years to reach the distance of Earth's orbit around the Sun, but it would never reach us. The interstellar medium, the thin gas that fills the space between stars, would slow and dissipate the blast wave long before it traveled 700 light-years. The remnant would eventually become one more shell of expanding gas in the galaxy, merging with the interstellar medium over thousands of years. Let that sink in. The most spectacular astronomical event that any human alive today might potentially witness in their lifetime would be entirely harmless. A cosmic explosion of almost incomprehensible power, delivering a visual display that would transform the night sky for a year or more, and it would do absolutely nothing to Earth. No radiation damage, no ozone depletion, no blast wave, no danger of any kind. We would simply watch. We are in the perfect seat, close enough to see the supernova in extraordinary, unprecedented detail, close enough to detect thousands of neutrinos, measure gravitational waves, and observe the event across the entire electromagnetic spectrum, and far enough away to be completely, utterly, magnificently safe. It is as if the universe placed us at exactly the right distance to witness one of its grandest events without being harmed by it. But the deeper truth is not about danger or the lack of it. The deeper truth is about meaning. The explosion of Betelgeuse would be more than a scientific event, more than a spectacle, more than a record-breaking observation. It would be a reminder, visible to every person on Earth, of processes that we rarely think about, but that are as fundamental to our existence as the ground beneath our feet. Every atom of carbon in your body was forged in the core of a star that died before Osborn was born. That is a simple statement of nuclear astrophysics, but its implications are staggering. The carbon that forms the backbone of your DNA, the carbon in the proteins of your muscles and the neurons of your brain, the carbon in the food you eat and the air you exhale, all of it was created inside a star, in a fusion reaction occurring at temperatures of hundreds of millions of degrees, deep inside a stellar core that no longer exists. And when that star exploded, it scattered its enriched material into the surrounding space, where it drifted for millions of years, mixing with hydrogen clouds, until gravity pulled it together again into a new star, new planets, new chemistry, and eventually new life. Every atom of oxygen you breathe was created in the same kind of nuclear fusion that is occurring inside Betelgeuse right now. The iron in your blood, the calcium in your bones, the phosphorus in the double helix of your DNA, the potassium that drives the electrical signals in your nervous system, the zinc in the enzymes that catalyze your metabolism. All of these were synthesized in the cores and explosions of massive stars that lived and died billions of years before you were born. We are, quite literally, made of the remains of dead stars. This is not a metaphor. It is not a poetic exaggeration. It is a chemical and nuclear fact, verified by decades of spectroscopic analysis, nuclear physics experiments, and computational modeling. The supernova of Betelgeuse, when it comes, will be a continuation of the very process that created us. The elements it forges and disperses, the heavier-than-iron elements produced by rapid neutron capture during the explosion, the silicon and oxygen and carbon ejected from the outer layers, will eventually become part of new stellar systems, new planets, new worlds. Perhaps, millions or billions of years from now, new forms of life. This idea, called stellar nucleosynthesis, was first articulated in a comprehensive and rigorous form in a landmark 1957 paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. The paper, known informally as B²FH after the initials of its authors, laid out in meticulous detail the nuclear physics by which elements heavier than hydrogen and helium are created inside stars. It showed that the entire periodic table, from the lightest elements to the heaviest, is a product of stellar evolution and stellar death. Without supernovae, the universe would contain nothing but hydrogen, helium, and trace amounts of lithium, the three elements produced in the first few minutes after the Big Bang. No carbon, no oxygen, no nitrogen, no iron, no silicon, no planets, no water, no chemistry, no life. The universe would be a diffuse, featureless expanse of the simplest atoms, capable of forming stars but nothing else. Supernovae changed that. They enriched the universe with complexity. They seeded the interstellar medium with the raw materials for rocky planets, liquid water, organic molecules, and eventually, organisms capable of looking up at the sky and wondering where they came from. Betelgeuse is participating in this process right now. Its core is building heavier and heavier elements with each successive fusion stage, and when it finally explodes, the shock wave will trigger a burst of rapid neutron capture reactions called the R process that will create elements even heavier than iron, elements like gold, platinum, uranium, and thorium, and fling them into space at thousands of kilometers per second. There is something vertiginous about this realization. We are temporary arrangements of atoms that were forged in ancient stellar explosions, sitting on a planet made of the debris of dead stars, orbiting a star fueled by the same physics that will destroy Betelgeuse, and we are watching that destruction approach with full knowledge of the mechanisms involved. We are the universe observing its own creative destruction. We are matter that has organized itself to the point where it can contemplate the processes that created it and anticipate the processes that will continue to create after we are gone. The philosophical weight of Betelgeuse extends beyond the chemistry. Consider the timescales involved. Betelgeuse was born roughly 8 to 10 million years ago, from the gravitational collapse of a dense region within a molecular cloud. At that time, our ancestors were small, tree-dwelling primates in the forests of what is now Africa. The Mediterranean Sea was being flooded through the Strait of Gibraltar. The Himalayas were still rising, pushed upward by the slow collision of the Indian and Eurasian tectonic plates. The entire arc of human evolution, from the first bipedal hominids to the construction of particle accelerators and space telescopes, has unfolded during the lifetime of this single star. Betelgeuse has been burning in the sky for the entire duration of our becoming. It was there when Homo erectus walked out of Africa. It was there when Neanderthals painted caves in Europe. It was there when the first cities were built in Mesopotamia, when the pyramids rose in Egypt, when the first astronomers in Babylon began recording the movements of the planets. And it may still be there when our descendants leave this planet and begin to settle other worlds. Or it may not. That is the point. The death of Betelgeuse could come at any time. Tomorrow. In 1,000 years. In 100,000 years. We live our lives on a timescale that is almost infinitely small compared to the life of this star. And yet we are the ones watching. We are the ones asking. We are the brief, curious witnesses to an event that spans millions of years, and that will conclude in a fraction of a second. It is worth noting that the history of supernova observation has already taught us to be humble about our expectations. When SN 1987A erupted in the Large Magellanic Cloud, astronomers were surprised to discover that its progenitor star was not a red supergiant at all. It was a blue supergiant, a hotter, more compact star called Sandulac -69202. For decades, the theoretical models had predicted that core collapse supernovae should come predominantly from red supergiants. The discovery that a blue supergiant could also explode forced a significant revision of our understanding of the final stages of massive stellar evolution. It turned out that the progenitor had likely been a red supergiant at an earlier phase, but had contracted and heated up before the final collapse, perhaps due to mass loss or binary interactions. The lesson was clear. Stars do not always behave the way our models predict, and the moment of death can arrive in forms we did not anticipate. Betelgeuse, for all its fame and familiarity, could yet surprise us. The explosion, when it comes, may not match our carefully constructed simulations. The remnant may not be what we expect. The light curve, the neutrino signal, the gravitational wave signature, all of these could contain features that challenge our theoretical frameworks and force us to revise what we think we know. That possibility is not a source of anxiety. It is a source of excitement. It is the reason we watch. There is a particular kind of awe that comes from holding these two timescales in your mind simultaneously. The millions of years that Betelgeuse has been burning, and the fraction of a second in which it will die. The billions of years over which stellar nucleosynthesis has been enriching the universe, and the few decades of a human life during which one might witness the next installment of that process. We exist at the intersection of the cosmic and the momentary. We are brief flickers of consciousness in a universe that operates on timescales we can describe mathematically but cannot truly feel, and yet we try. That is what makes the story of Betelgeuse so compelling. It is not just a story about a star. It is a story about the relationship between the observer and the observed, between the temporary and the enduring, between the small and the vast. Every time a human being looks up at Orion and identifies that reddish point of light and knows, however dimly, that it is a dying star, something remarkable is happening. A pattern of matter that will exist for perhaps 80 years is contemplating a pattern of matter that has existed for 10 million years, and both patterns are made of the same stuff. Both are temporary. Both are part of the same ongoing process of cosmic evolution. The gold in the ring on your finger was almost certainly forged in a neutron star merger or in the R process of a supernova explosion billions of years ago. The platinum in the catalytic converter of your car, the uranium in a nuclear reactor, the thorium in the mantle of a camping lantern, each of these elements was created in a moment of extreme violence, in the final seconds of a dying star, or in the collision of two neutron stars. and then dispersed into space, where it drifted for eons before being incorporated into the disk of gas and dust that became our solar system. The jewelry we wear, the technology we build, the medicine we take, all of it is a downstream consequence of stellar death. We do not merely observe supernovae from a distance. We are built from their products. We are the consequence of the very process we are studying. This circularity is not a coincidence. It is a necessary feature of a universe governed by the laws of physics as we understand them. Stars must form, burn through their fuel, and explode in order to create the elements necessary for rocky planets and complex chemistry. Complex chemistry must arise in order to produce self-replicating molecules. Self-replicating molecules must evolve over billions of years in order to produce organisms capable of looking up at the sky and wondering where the elements in their bodies came from. The chain is unbroken. It stretches from the first generation of massive stars in the early universe, which contain nothing but hydrogen and helium and trace lithium, through billions of years of stellar evolution and enrichment, through the formation of our Sun and its planetary system, from the debris of earlier stellar generations, through the origin and evolution of life on Earth, all the way to this moment, when you are reading or hearing these words and thinking about a red supergiant star on the shoulder of Orion. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. And Betelgeuse, in its slow and unstoppable decline, mirrors that impermanence on a cosmic scale. It is a reminder that nothing lasts. Not stars, not species, not civilizations, not individual lives. But it is also a reminder that endings are not truly endings. They are transformations. The matter that is Betelgeuse today will become the raw material for something new tomorrow. And the matter that is us today was the raw material of something ancient yesterday. The death of Betelgeuse is not an ending. It is a transformation, a recycling of matter on a cosmic scale, a necessary step in the ongoing process by which the universe builds complexity out of simplicity, structure out of chaos, meaning out of physics. And we are here to see it. That may be the most extraordinary thing of all. What does Betelgeuse mean for us? Not as scientists, not as astronomers, as humans, as a species that has looked up at the night sky for as long as it has been able to wander. The most immediate implication is practical. If Betelgeuse goes supernova within the next few centuries, it will be the most significant astronomical event in recorded human history. It will be visible to every person on Earth who can look up at the sky. It will appear in every culture's firmament. It will be photographed, live-streamed, analysed in real time by every telescope, detector and satellite in existence. The data it provides will revolutionise our understanding of stellar death, supernova physics, neutron star formation, and the origin of the heavy elements. A single event will answer questions that have been open for decades and raise new questions that we have not yet thought to ask. The supernova would provide the first opportunity in the history of modern science to observe the full multi-messenger signature of a core collapse supernova at close range. Neutrinos, gravitational waves, electromagnetic radiation across the entire spectrum from radio waves to gamma rays, all arriving in a choreographed sequence that reveals the physics of the collapse in exquisite detail. The neutrinos would arrive first, several hours before the optical brightening, providing advance warning to every observatory on the planet and in orbit. Then, the gravitational wave signal, carrying information about the dynamics of the core bounce and the formation of the proto-neutron star. Then the ultraviolet flash as the shock wave breaks through the stellar surface. Then the visible light, rising over days to its extraordinary peak. Then the infrared glow of cooling debris. Then the radio emission from the expanding blast wave, interacting with the circumstellar material that Betelgeuse has been shedding for millennia. The last time a supernova occurred close enough for detailed study, SN 1987A, in the Large Magellanic Cloud, the astronomical community had only a handful of neutrino detectors and no gravitational wave observatories at all. The 25 neutrinos detected from that event were enough to confirm the basic theoretical picture of core collapse, but they were far too few to constrain the detailed physics. Today we have a global network of neutrino detectors, the LIGO Virgo Cagra Gravitational Wave Network, operating at unprecedented sensitivity, space-based gamma-ray and X-ray observatories, including the Fermi Gamma-ray Space Telescope and the Chandra X-ray Observatory, ground-based optical and radio telescopes of extraordinary power, including the Vera C, Rubin Observatory and the Square Kilometre Array, and a generation of astronomers who have spent their careers preparing for exactly this event. We are, for the first time in history, truly prepared for a galactic supernova. We just do not know when it will come. But there is a deeper implication, one that extends beyond the scientific and into the realm of human experience. Betelgeuse forces us to confront a particular kind of cosmic awareness. We are conscious of a specific event that is certain to occur but unpredictable in its timing. It is like knowing that an earthquake will happen on a particular fault line without knowing when it will strike, except the fault line is a star 700 light-years away, and the earthquake is an explosion that will outshine 10 billion suns. This awareness has a strange psychological effect. It makes the night sky feel alive in a way that it does not normally feel for most people. When you look at Orion and see that red point on the left shoulder, you are not looking at a static decoration. You are looking at a live process. You are watching a star that is actively evolving, actively changing, actively approaching its end. Most of the stars in the sky appear eternal, unchanging, fixed in their positions and their brightness, as if painted on a celestial dome. Betelgeuse shatters that illusion. It reminds us that the sky is not a ceiling. It is a window into a universe of constant change, where stars are born, live, and die on timescales that dwarf all human history, but that are, in cosmic terms, heartbreakingly brief. There is a concept in Japanese aesthetics called mono no aware, often translated as the pathos of things, or an empathy toward things. It describes the bittersweet awareness of impermanence, the beauty that exists precisely because something is fleeting. A cherry blossom is beautiful, not despite the fact that it will fall, but because of it. Its transience is inseparable from its beauty. The falling of the petals is not a tragedy. It is the completion of the blossom's story. Betelgeuse embodies this quality on a cosmic scale. It is beautiful because it is dying. Its red light, its immense and swollen size, its turbulent and restless surface, its massive ejections of material into the surrounding void, all of these are symptoms of its decline. And the supernova, when it comes, will be the most spectacular moment of beauty it will ever produce. A final incandescent farewell that will outshine everything else in the galaxy before fading over months and years into a quiet remnant. The cherry blossom falls, the star explodes, and in both cases, the ending is not separate from the beauty. It is the culmination of it. We are living in the pause before that moment, the waiting, the anticipation, the long, slow inhale before the exhale that will change the sky forever. And there is something uniquely human about this experience. No other species on Earth can look at a star and understand that it is dying. No other species can anticipate the explosion, calculate its brightness, model its physics, or feel the mixture of wonder and melancholy that comes from knowing we are witnessing the end of something that has existed for millions of years. Dogs do not contemplate supernovae. Trees do not measure the spectra of red supergiants. Dolphins do not calculate neutrino cross-sections. Only we do. Only we can. And there is something both magnificent and lonely about that fact. We are the only species on this planet, and possibly one of very few in the entire galaxy, that can look at a point of light in the night sky and understand that it is a sphere of plasma 1.2 billion kilometers across, burning through its final reserves of nuclear fuel, destined for a catastrophic collapse that will briefly outshine the combined light of 10 billion ordinary stars. This is what separates us from the cosmos that created us. We are the part of the universe that watches, that wonders, that mourns, that celebrates. And in that watching, that wondering, that mourning, that celebrating, we create a kind of meaning that the universe itself does not possess. The universe does not care about Betelgeuse. It does not care about supernovae or nucleosynthesis, or the origin of the elements. It simply is. Matter and energy, interacting according to the laws of physics, without purpose, without intention, without awareness. But we care. And in caring, we add something to the universe that was not there before. A witness, a perspective, a narrative. a story told by the products of stellar evolution about the process of stellar evolution. Every generation of humans has looked up at Orion and seen Betelgeuse. Every generation has seen the same red light, the same constellation, the same pattern against the darkness. The ancient Sumerians saw it, the builders of Stonehenge saw it, the navigators of Polynesian canoes saw it, the astronomers of the Islamic Golden Age saw it, Shakespeare saw it, Newton saw it. Every generation has seen the same star, and every generation has assigned it meaning according to their understanding of the world. But our generation is the first to truly understand what we are looking at, the first to know that this light comes from a dying star, the first to comprehend the physics of what will happen when it finally lets go, the first to grasp that the elements in our bodies were forged in events exactly like the one we are waiting for, and potentially the first, or among the first, to see it happen. There is a kind of privilege in that knowledge, and a kind of responsibility. When Betelgeuse explodes, it will be a moment that unites the entire world in a shared experience. Every person, in every country, on every continent, will be able to look up and see the same extraordinary light. In a world increasingly divided by politics, ideology, geography, and identity, the supernova of Betelgeuse would be a reminder of something that transcends all of those divisions. We share the same sky, we share the same universe, we are all made of the same stellar material, forged in the same kinds of explosions, subject to the same laws of physics, and destined for the same eventual return to the elements from which we came. The supernova would also be a moment of profound scientific collaboration. Astronomers in every country would share data in real time. Neutrino physicists in Japan would compare notes with gravitational wave scientists in the United States, and radio astronomers in Australia, and optical observers in Chile. The event would transcend national boundaries, institutional rivalries, and disciplinary silos. It would be a reminder that the most important questions in science are not owned by any single nation or institution, but belong to all of humanity. And perhaps most importantly, the supernova would be a reminder that we are small, not insignificant, but small. Small in the sense that the universe is vast beyond our intuition, and old beyond our comprehension, and powerful beyond our experience. Small in the sense that the forces that shape the cosmos operate on scales that make human concerns look, if not trivial, then at least local. The explosion of a single star, releasing more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime, puts our daily struggles into a certain perspective, not a diminishing perspective, a clarifying one, a perspective that says, you are part of something much larger than yourself, much older than your civilization, much more enduring than your species, and that larger thing is beautiful. There is also a practical legacy to consider. The supernova remnant left behind by Betelgeuse will become one of the most studied objects in the sky for centuries, perhaps millennia, to come. The expanding shell of gas will glow with the light of ionized elements, revealing the detailed composition of the star's outer layers and the products of its final explosive nucleosynthesis. The remnant will serve as a laboratory for studying the physics of shock waves, particle acceleration, magnetic field amplification, and the interaction between supernova ejecta and the surrounding interstellar medium. It will be visible in X-rays, in radio waves, in the infrared, and eventually in visible light, as the initial flash fades and the slower expanding debris begins to interact with the material that Betelgeuse shed during its millions of years as a red supergiant. At the center of the remnant, depending on the mass of Betelgeuse, at the moment of collapse, there will be either a neutron star or a black hole. If it is a neutron star, it may be detectable as a pulsar, spinning rapidly and emitting beams of radio waves that sweep across the sky like a lighthouse. If it is a black hole, it will be invisible except through its gravitational influence on surrounding material. Either way, the remnant will be a monument to the star that once was, a fossil record of a life that spanned millions of years and ended in a fraction of a second. Future generations of astronomers will study this remnant with telescopes and instruments that we cannot yet imagine. They will extract information from it that we do not yet know how to seek. And they will know that the people who first witnessed the explosion, who first saw the light arrive, who first detected the neutrinos and the gravitational waves, were the people alive in our era. We will be remembered not for our politics or our conflicts or our technology, but for the cosmic event that happened to occur during our watch. That is a strange and humbling and deeply moving form of historical significance. And we are all, like Betelgeuse, temporary. So what remains? What is left to say about a star that has been saying everything it needs to say for millions of years, broadcasting its story in light across the void for anyone with the patience and the curiosity to listen? Perhaps only this: Betelgeuse will explode. That much is certain. The hydrogen is gone. The helium is being consumed. Carbon, neon, oxygen, silicon, each will burn in turn, each faster than the last, until the iron core grows too heavy and the delicate balance between gravity and pressure breaks for the final time. The core will collapse at a quarter of the speed of light. The infalling material will bounce off the newly formed neutron star. The shock wave, revived by a torrent of neutrinos, carrying away the gravitational binding energy of the core, will tear through the outer layers of the star. And for a brief, glorious moment, a single star will shine with the light of 10 billion suns. We do not know when this will happen. It could be tomorrow. It could be in 100,000 years. The uncertainty is not a failure of science. It is an honest acknowledgement of how much we still do not know about the internal workings of the most massive and unstable stars in the universe. We cannot see through hundreds of millions of kilometers of superheated plasma to observe the core directly. We cannot measure the precise mass with sufficient accuracy to pin down the evolutionary state. We cannot determine whether the star has already progressed beyond carbon burning into the rapid-fire final stages that precede collapse. And that honesty, that willingness to say we do not know, is itself a kind of strength. It is the foundation upon which all genuine understanding is built. The history of science is not a history of certainties. It is a history of increasingly refined uncertainties, of narrowing the gap between what we know and what we do not, one observation and one calculation at a time. When the light arrives, whenever it arrives, it will have travelled for 700 years across the near vacuum of interstellar space before it reaches our eyes. 700 years of silence, followed by a burst of brilliance that will transform the night sky and alter the shape of one of the most recognizable constellations in human history. The delay is itself a kind of metaphor. The most important events often happen long before we become aware of them. The consequences travel toward us at the speed of light, and we can only wait. We cannot hurry the message. We cannot slow it down. We can only be ready when it arrives. In the meantime, Betelgeuse is there, right now, tonight. If the sky is clear and the season is right, you can walk outside and look up at Orion, and you will see it. That reddish point of light on the left shoulder of the hunter. It does not look like a star on the verge of annihilation. It looks peaceful, steady, familiar. It looks like it has always been there and always will be. But it has not always been there, and it will not always be there. It was born from a cloud of gas and dust, roughly 8 to 10 million years ago, in a region of active star formation that may no longer exist in recognizable form. It ignited its hydrogen fuel and joined the main sequence as a hot, blue, massive star, burning with a fierce intensity that was millions of times brighter than our sun. It lived fast, consumed its fuel at a prodigious rate, and swelled into the vast, cool, red supergiant we see today, 800 times the diameter of our sun, engulfing the orbits of Mercury, Venus, Earth and Mars. A star so large that light itself takes over an hour to travel from one side to the other. And all of that immensity, all of that power, all of that furious burning, is a prelude to a single moment of collapse that will last less than a second. Stars do not fade away. Not stars like Betelgeuse. They do not gently dim and cool and drift into obscurity. They detonate. They transform. They take everything they have built over millions of years, every layer of fused elements, every shell of processed material, every atom of carbon and oxygen and silicon and iron, and they release it in a fraction of a second in an explosion that briefly outshines an entire galaxy. And in that release, they create something new. New elements that did not exist before the explosion. New isotopes forged in the intense neutron flux. New possibilities for chemistry, for geology, for biology, for life itself. The calcium in a child's growing bones. The iron in the blood that carries oxygen to a dreaming mind. The carbon in the ink of a poem, or the graphite of a pencil, or the diamond in a ring. The silicon in a processor that maps the heavens and searches for exoplanets. All of it forged in moments like the one that awaits Betelgeuse. We are watching the end of a star, but we are also watching the beginning of everything that comes after. Every supernova is simultaneously a death and a birth, an ending and a seeding, a destruction so complete that nothing of the original star survives in its previous form, and a creation so fundamental that without it, the universe would be a barren expanse of hydrogen and helium, devoid of complexity, devoid of structure, devoid of planets, devoid of oceans, devoid of us. Betelgeuse does not know we are watching. It cannot know. It is a sphere of plasma, governed by the laws of physics, indifferent to observers, incapable of awareness or intention. It does not burn for our benefit. It does not pulse for our entertainment. It does not prepare for its death with any sense of drama or purpose. It simply follows the physics. Gravity pulls inward. Pressure pushes outward. Fusion produces energy. Energy is radiated away. The fuel diminishes. The balance shifts. And eventually, inevitably, irrevocably, the balance fails. But we are watching. And in watching, we complete a circle that spans billions of years and billions of light years. The elements that were forged in ancient supernovae, in stars that died long before our sun existed, became the raw material for molecular clouds, for protoplanetary disks, for rocky planets, for oceans, for amino acids, for proteins, for cells, for organisms, for brains, for minds. And those minds now look back at the stars that made them and understand the process. The universe created creatures capable of witnessing their own origin story. That is not a poetic embellishment. That is not a metaphor dressed up in the language of science. That is what happened. That is the plain, verifiable, extraordinary truth. When Betelgeuse finally lets go, the sky will change. Orion will lose its shoulder. A new light will burn where the old one faded, brighter than anything anyone alive has ever seen from beyond our solar system. For weeks it will rival the moon. For months it will outshine every star. And then, over the following year or two, that light will fade, slowly and gracefully, leaving behind a glowing remnant, a neutron star or perhaps a black hole, and an expanding cloud of enriched gas that will drift through interstellar space for millennia, carrying with it the raw materials for new worlds. Somewhere, millions of years from now, that gas will encounter a molecular cloud. It will merge with the hydrogen and helium already present. The combined cloud will grow denser. Gravity will begin to pull it together. A new star will form at the center. Planets will coalesce from the surrounding disk of debris. The elements of Betelgeuse's destroyed body, mixing with material from dozens of other stellar sources. And on one of those planets, perhaps, if the conditions are right, if the chemistry allows it, if enough time passes, something will look up at the night sky and wonder where it all came from. The answer will be the same as ours. It came from the death of stars, from the violence and beauty and necessity of a universe that builds complexity by destroying simplicity, that creates order by unleashing chaos, that makes life possible through acts of annihilation so powerful they defy human comprehension. From the ashes of Betelgeuse, and from the ashes of a billion other stars just like it, scattered across a universe so vast that it contains more stars than there are grains of sand on every beach on Earth. Tonight, if you can, go outside, find Orion, look at the red star on the shoulder, and know that you are looking at something ancient, something enormous, something that is preparing for a transformation so powerful that it will be felt across 1,000 light years of space. Know that the atoms in your body were forged in stars just like this one. Know that you are connected to that red point of light by a chain of cause and effect that stretches back to the very first generation of stars, billions of years ago, in a universe that was younger and simpler and darker than the one we inhabit today. It has been there for as long as humans have had eyes to see it. It will not be there forever. Nothing is. And in that simple, inescapable fact lies the most profound truth that the night sky has to offer. Everything changes. Everything ends. And everything, in ending, makes room for something new. The shoulder of Orion is glowing red tonight. It has a story to tell. And if you are patient, if you are watching, if you are willing to sit with the silence and the darkness and the immensity of it all, you might just be alive when it tells it.